Hello there and welcome to Science for Sleep, where curiosity gets comfortable and the universe quiets down enough for us to take a gentle look around. Tonight, we're drifting into a question that sounds almost too simple at first, but the more you sit with it, the larger it becomes. In fact, it becomes so large that it stretches out farther than any distance you've ever walked, farther than the space between stars, and farther than the soft glow of your reading lamp has ever reached. We're exploring why the universe, this place that holds everything we've ever known, everything we've ever imagined, and everything we've ever wondered about, is mostly empty. It's a strange thought if you haven't visited it in a while. We go through our days surrounded by things: rooms, streets, cities, trees, clouds, people. Our world feels full. Even when a room is quiet or a night is still, there's always something nearby. A cup on the table, a pair of shoes by the door, the hum of a refrigerator, the whisper of cars passing outside. It all gives the impression that existence is packed, layered, overflowing. So, it can be a little surprising to realise that this sense of fullness is extremely rare on the grander scale of things. If you zoom out far enough, far beyond the walls around you and the familiar shape of your home, you begin to enter a world where the spaces between objects are immense. You could travel for trillions of kilometres and never hit a single thing. You could float for ages and never collide with a grain of dust. Out there, emptiness isn't the exception, it's the rule. Before we settle into why that is, I'm curious. Where are you listening from tonight? Somewhere quiet? Somewhere bright? Somewhere familiar? And what time is it for you right now in your corner of this very full-feeling world? I always find it comforting to know that, even though we're scattered across time zones and landscapes, we're meeting right here in the same moment, sharing the same curiosity, letting the same thoughts drift in. It makes this whole thing feel a little less empty somehow. And if you find this gentle dive into the universe relaxing or calming, or simply a nice companion to the end of your day, I'd be grateful if you'd like the video or subscribe. It helps this little quiet corner reach others who might need a soft place to land as well. Now, take a breath, get comfortable, and let's begin this slow journey into the space between almost everything. The first thing to understand when we talk about emptiness is that the universe didn't start out looking this way. It didn't begin as a vast, yawning expanse with the occasional star or galaxy sprinkled across it. In the very earliest moments of existence, things were packed tightly together. Not just tightly, but unimaginably so. Everything you see now, everything you've ever heard of, every atom in your body, every photon of light dancing across your room right now, was once compressed into a state so dense and hot that the words crowded and full don't quite do it justice. It wasn't empty at all. It was more like a pressure cooker of potential. Then, very suddenly, and with extraordinary speed, it expanded. Not into space, but as space. And as this expansion continued, everything that would one day become stars, planets, galaxies, and eventually you slowly drifted apart. As the universe grew, the room between things increased. The expansion didn't stop. It kept stretching and stretching, like someone pulling on the corners of a vast cosmic bedsheet. As it stretched, matter clumped in certain places but left enormous regions in between where almost nothing settled. It's a bit like dropping handfuls of sand across a huge floor. The grains cluster in some spots, forming little piles, but most of the floor stays empty, simply because the space is so vast and the grains are so few in comparison. The universe is similar. There are clusters of matter, galaxies gathering in groups and threads, but the gaps between those threads are enormous. When you think about the distances involved, even the clusters begin to feel lonely. It's important to remember that when we say empty, we don't mean completely vacant. Even in the quietest stretches of space, you can find the occasional rogue particle drifting by. A lonely proton, a stray electron, a photon that left its home millions of years ago, still travelling onward. But these bits are so spread out that for practical purposes, space behaves like it's empty. If a single particle passes through a cubic meter of space every few hours, that cubic meter is for all intents and purposes a void. If you were to stand inside that void, which you couldn't, because there's no ground or place to stand, you wouldn't feel anything around you. No pressure, no sound, no wind, no scent, just the steady presence of nothing. It's different from quiet. Quiet still has air and warmth and the soft vibration of life. This is more like the absence of everything your senses expect. The emptiness would be so complete that your mind might struggle to make sense of it. And yet this near-nothingness fills most of the universe. It's natural to wonder why matter is so rare. Why isn't the universe more crowded? Why didn't things gather more closely? Why isn't there more stuff in general? One reason is that the universe simply doesn't need much matter to operate. The forces that shape galaxies and stars don't require space to be densely packed. Gravity can work across enormous distances. A star and a planet don't have to touch or sit close together for gravity to bind them. They just need to be within each other's reach, and reach can be very, very long. Another reason is time. The universe has had an incredible amount of time to expand. It's been stretching for billions of years, and with every passing moment the distances grow larger. The stretching isn't just happening between faraway galaxies. It's happening everywhere, even in places where we don't notice it. We don't feel it at home because gravity holds our environment tightly enough that expansion can't pry it apart. But on the grand scale, where galaxies sit loosely in clusters, the expansion has more room to operate. So the universe grows, and as it grows, the spaces widen. This widening is still happening right now. Even as you listen to these words, the universe is expanding. The galaxies are drifting farther apart, not because they're moving through space like travellers crossing a desert, but because the space between them is literally increasing. It's a bit like drawing a few dots on a balloon. When the balloon inflates, the dots grow farther apart even though they're not moving on their own. They're being carried by the surface stretching beneath them. The same thing happens with galaxies. They're dots on the cosmic balloon, and the more the balloon expands, the emptier things become. People sometimes imagine space as a big dark room with scattered lamps representing stars. But that image is misleading because it suggests the room itself is fixed and waiting to be filled. In reality, the room keeps getting bigger, and not just a little bigger. It's expanding faster than you might expect. The amount of space between stars is enormous already, but the expansion means it will be even greater in the future. As we drift deeper into this topic, you'll notice something interesting. The more we talk about the emptiness of the universe, the more it reveals about the parts that aren't empty. The emptiness helps define the structure. It explains why galaxies look the way they do, why stars form where they form, why planets orbit in the patterns they follow. Even the spaces inside atoms have their own version of emptiness. When you picture an atom, you might think of it as a compact cluster, but in truth, atoms are mostly empty. The nucleus is tiny, a dense speck at the centre, and the electrons that surround it are so small and so far from the nucleus relative to their size that the atom is almost entirely void. A seemingly solid object, like a rock or a chair or the floor beneath you, is mostly empty space held together by forces rather than matter itself. It's curious to realise that the emptiness in the universe isn't limited to the vast cosmic scales. It's inside the objects we touch every day. Even your own body has far more empty space than material. But because the forces at play are strong and steady enough, we experience these things as solid, reliable, part of a full world. At the atomic level, emptiness doesn't feel like anything at all. It's simply the space where particles are not. This idea that emptiness is woven into everything might feel a little strange at first, but as we move forward you'll see that the universe uses emptiness as part of its structure, not as an accident or a leftover. The emptiness gives things room to form, room to move, room to exist at all. Without the enormous voids, the rare bits of matter wouldn't be able to gather and build the galaxies and stars that make the night sky look the way it does. The emptiness is what allows shape and motion and light to happen in the first place. So, as we continue, keep in mind that the universe didn't choose emptiness as a flaw or a mistake. It's simply the result of how space expands, how matter clumps, and how forces interact. The emptiness is part of the design, whether intentional or not, and far from being a cold or lonely concept, it can be strangely reassuring. Emptiness gives everything else a place to be. When you look around the environment you're in right now, the word full probably fits better than the word empty. Even if you're in a quiet room or lying in bed, there's always something nearby. A pillow, a wall, a blanket, a lamp, the shape of your hand resting near you. You see spaces between objects, but those spaces are small and familiar. You never get the impression that your surroundings are mostly nothing. We move through daily life assuming that the world is built out of matter, that existence is dense, layered, packed with things. It's an understandable assumption because everything we interact with seems solid and fully present. That impression, though, turns out to be one of the most misleading parts of being human. Our senses evolved to understand the world at a size that helps us survive. We see objects large enough to matter to us. We hear sounds that come from nearby sources. We feel surfaces because our bodies need to navigate them. Everything in our sensory world reinforces the idea that reality is structured, filled in, continuous. So when someone says that the universe is mostly empty, or that matter is rare, it doesn't quite match what we've experienced. It feels like an exaggeration, or a strange bit of scientific humour. Yet, this empty nature is one of the clearest truths about the cosmos. To understand why emptiness is the norm, you have to start by noticing how limited our perspective is. Imagine for a moment shrinking down smaller and smaller, until the room around you becomes enormous. If you could travel through the air at that size, you'd find that what looks like open air to your normal eyes is not thick or crowded. It's mostly space dotted with molecules far apart relative to their size. Air feels full to us only because our bodies interact with trillions of molecules at once. But the molecules themselves barely touch each other. In a cubic metre of air, the individual particles occupy only a minuscule fraction of the volume. The rest is empty. But because we live among them, surrounded by their constant movement, we interpret the air as dense. Now imagine shrinking even further until you're the size of an atom. At that point, the illusion of fullness completely disappears. The typical atom is almost entirely open interior. If you place the nucleus on a table and tried to find the nearest electron, you'd have to look very far away relative to the nucleus's size. So far that if you scaled the nucleus to the size of a grain of rice, the electron's orbit could stretch out to the distance of a large cathedral, and yet the atom still counts as stuff to us, because the forces between its particles are strong enough to resist pressure and behave like a solid. But structurally, the atom doesn't resemble a solid object at all. It resembles a tiny dot surrounded by huge empty gaps where nothing occupies the space. This same pattern continues upward. Molecules are sparse relative to their size. Organisms, plants, animals, people are made from atoms separated by empty interior. Objects that appear solid are mostly spaces where particles are not located. If you took all the actual matter in your body and compressed it down until there were no empty gaps inside the atoms, your entire mass would shrink to something smaller than a grain of sand. It wouldn't be recognizable as a person. Everything that gives you shape, your height, your volume, your presence, is mostly a structure held together by forces acting across empty distance. Once you understand how emptiness exists in the objects we touch and rely on, it becomes easier to make sense of why the universe behaves the same way but on a much larger scale. The illusion of fullness comes from our human scale, not from the actual quantity of matter. We live in an environment where our senses respond to forces, pressures and interactions that occur even when matter is sparse. Our entire experience of existence is built out of the rare places where matter has collected. But on cosmic scales, No one deals with the illusion. The emptiness is obvious from the moment you begin to measure distances between objects. Consider the solar system. The sun is enormous, glowing with such intensity that it influences everything around it. The planets orbit in wide, predictable paths. The inner planets often get attention because they're closer to each other and feel familiar in diagrams. But these diagrams make a crucial mistake. They show planets large enough to see and place them near each other, so the drawing makes sense. If you ever try to draw the solar system to scale, you immediately notice the problem. If the Earth is the size of a small bead, the Moon is a tiny speck a short distance away, and the Sun is a large ball sitting far off in one direction. However, the nearest planets are shockingly distant. Even Mars, our closest neighbour beyond the Moon, sits so far away on this scale that the space between Earth and Mars would easily hold tens of thousands of Earths laid side by side. And that gap between planets isn't filled with debris or gas or dust. It's emptiness. This is why spacecraft can travel for months without hitting anything. Space isn't a crowded highway. It's more like an open desert on a scale our minds aren't designed to picture. Even in places where matter gathers, planetary systems, asteroid belts, regions with comets, the material is widely separated. Asteroids and comets are so spread apart that it's rare for anything to collide unless something shifts their orbits. The phrase asteroid belt makes it sound like a rocky ring packed tightly around a star, but the reality is far from that. The objects in an asteroid belt are spaced so widely that you could travel through one without even glimpsing an asteroid nearby. The illusion continues when we look at galaxies. A galaxy contains billions or even trillions of stars, all orbiting around a central region. Pictures of galaxies make them look thick and luminous. They resemble cities from above, their arms swirling like bright highways. But those images also compress scale. If you stood next to a star inside a galaxy and tried to find the nearest star, you'd be searching over immense distances. The nearest star to our Sun is so far away that if the Sun were the size of a lantern, the closest star would be another lantern placed in another country. Between them, there would be nothing. No structures, no crowds, no walls, just space stretching onward without interruption. The reason galaxies look full is because we see them from such a distance that the light from their stars blends together. Millions of tiny points blur into smooth shapes. Up close, however, galaxies are nearly empty. Their stars roam through vast spaces, held together by gravity but barely influencing each other directly. This emptiness isn't an accident, it's necessary. If matter were denser, stars would collide more often. Orbits would become unstable. The delicate balance of energy, motion, and formation processes would break. The emptiness gives stars the room they need. The emptiness prevents destructive overcrowding. The emptiness is the foundation that lets everything coexist without chaos. Even the densest objects in the universe have empty surroundings. A neutron star is extraordinarily compact, a city-sized sphere with the mass of a sun. But despite its incredible density, the area around it is almost completely empty. A neutron star could travel through the galaxy for millions of years without touching anything other than stray particles drifting near it. It could pass through enormous regions without hitting a cloud or a star. The universe is built so that even its extremes are surrounded by open distances. This distribution of matter didn't happen by chance. It's the result of the early universe expanding rapidly. When everything was tightly packed, the sudden expansion stretched the space so quickly that matter had no time to fill it. Matter didn't spread out evenly. It settled into small seeds where gravity could gather it, leaving enormous regions untouched. These regions became the cosmic voids, areas so large that you could fit thousands of galaxies inside them, yet containing almost nothing. The voids dominate the layout of the universe. They form the background against which galaxy clusters appear. If you could see the universe's structure as a giant map, you'd notice that matter occupies thin threads and knots. while most of the map remains an open expanse. When you understand this structure, the illusion of fullness feels gentler. It's not that our world lies to us. It's that our senses highlight the rare, dense areas, because those areas are where life emerges. The emptiness doesn't demand our attention. It doesn't change form. It doesn't shape itself into something we can hold. But it is just as real and far more abundant. There's something grounding about realizing that emptiness is not an unusual feature. It's not something rare or unnatural. It's the default state. Matter is the exception. It forms in clumps because gravity binds it, but it never fills space completely. The universe is not crowded because it never needed to be. The forces and processes that allow stars to form and planets to take shape work perfectly well without a crowded backdrop. In fact, they work better with room to move. This idea also helps explain why the night sky looks the way it does. When you look at the stars, you see points of light scattered across darkness. At first glance, you might imagine the sky is full of stars, but the darkness between those points isn't filled with hidden light or invisible objects. It really is mostly empty. The light you see has travelled for unimaginable distances to reach you. Each point of a light is a single star or a distant cluster. Everything between those points, millions of kilometres here, trillions there, perhaps even more, is space where nothing interrupted the path of the light. The illusion of fullness remains so strong because our minds naturally focus on the things that emit or reflect energy. We see stars, not space. We see planets, not the vast regions around them. We see the few places where matter gathers and behave as if those gatherings represent the rule rather than the exception. But the more you explore the universe, the more clear it becomes that matter is a rare visitor in the expanse. The universe is arranged in such a way that pockets of matter drift in enormous rooms of emptiness. And the structure isn't accidental. It's a result of the initial conditions and the ongoing expansion that continue shaping everything. The more we understand this, the less intimidating the emptiness becomes. It isn't a sign of loneliness or absence. It's simply the environment in which everything else exists. The fullness we experience in daily life is a local feature. It's the tip of the cosmic iceberg, supported by an underlying structure that stretches far beyond what we can intuitively imagine. If you want to understand how the universe ended up with more nothing than something, you eventually have to follow the story back to a time when space itself didn't look anything like it does now. The vast open stretches we picture today weren't always there. They had to be created. The emptiness had a beginning, and it didn't appear slowly or gradually. It arrived far more abruptly than most people imagine, in a way that's almost the opposite of the calm, quiet universe we see now. To understand how space became as spacious as it is, you have to look at a period so early and so compressed that our everyday understanding of time doesn't quite apply. The earliest moments of the universe weren't roomy. They weren't even truly space in the sense we usually mean. Everything that now stretches between galaxies was once compressed into a state far smaller than even the tiniest thing you've ever seen. It wasn't empty, and it wasn't quiet. The entire cosmos was dense and hot. It was so dense that you couldn't pick out individual particles or points. You wouldn't have seen structure, gaps, or separations. Everything was pressed together in a state that didn't leave room for emptiness at all. The forces that now govern stars, planets, and atoms weren't acting independently. They were fused into an indistinguishable whole. People often imagine this early universe as a kind of giant explosion, something bursting outward into surrounding space, but that image creates the wrong idea. There was no surrounding space for anything to burst into. There was only the universe itself, and that universe expanded from within, carrying everything with it. The important detail isn't that it exploded, but that it expanded. Expansion is the key to understanding why the universe became so spacious, because expansion doesn't require direction or emptiness. It simply stretches the fabric that everything sits on. Once that stretching begins, distances increase everywhere at once. The expansion wasn't slow or gentle. It happened in a way that is difficult to compare to anything in ordinary life. Within a fraction of a second, the universe grew by an enormous factor. Not by double or triple, not even by millions. It expanded unimaginably fast, in a process scientists refer to as inflation. Inflation wasn't a gradual swelling. It was an extreme and sudden stretching of space itself. If you were to picture it as a physical motion, it would be more like something snapping outward with incredible speed. This forced everything apart before matter even had time to organise itself. Inflation created the first enormous gaps, which later grew into the emptiness we see now. The interesting part is that inflation didn't create matter. It created space. The stretching happened so quickly that matter couldn't follow it evenly. Instead of filling the entire universe uniformly, matter stayed in slightly denser patches. Those patches were tiny variations in the early energy field. They weren't intentional. They weren't arranged. They were small irregularities amplified by the rapid expansion. Wherever the field was a little stronger, matter eventually collected. Wherever the field was weaker, space expanded more quickly and left behind emptier regions. These early variations planted the seeds for galaxies, clusters, and the large structures we see today. But between those seeds, the stretching created enormous gaps. To see how effective this stretching was, imagine having a room full of dust. If you expand the room just a little, the dust spreads out, but the room still looks dusty. Expand it drastically and suddenly the dust becomes sparse. It settles in tiny piles or trails, and almost the entire room becomes empty. If you expand the room further and keep doubling its size, eventually those dust particles become so scattered that you can't see most of them. The room is still full of dust in principle, but most of the space is just space. That's essentially what happened to the universe. Inflation made the room billions of times larger almost instantly, and the dust, the matter, didn't have time to spread evenly. It clumped in a few places, leaving the rest mostly empty. After inflation ended, the universe kept expanding, but much more slowly. This slower expansion allowed matter to begin forming the earlier structures. Hydrogen and helium dominated at first, along with small traces of a few other light elements. For hundreds of thousands of years, the universe was still too hot and too dense for atoms to form stable structures. It was a kind of glowing fluid where light couldn't travel freely. But even then, the seeds for emptiness were already set. The regions holding slightly more matter would eventually attract additional matter through gravity. These growing clumps would become galaxies and clusters. But everywhere else, the emptiness grew even more pronounced. It might help to picture the universe at this early stage as a scene where tiny overdense spots gather more material, while the underdense areas fall behind in density due to the overall expansion. Gravity pulls matter inward in some places, but it cannot pull emptiness inward. Emptiness doesn't bunch up or cluster. It behaves passively. It stretches along with the expansion. That's why emptiness increases over time, while matter stays in concentrated threads and knots. The stretching doesn't distribute matter evenly. It exaggerates differences. Regions already slightly emptier become larger voids. Regions slightly denser form stars and galaxies. The cosmos grows more structured and more spacious at the same time. Once atoms finally formed and the early universe became transparent to light, these small variations in density became easier to trace. Light from that era still exists today as the cosmic microwave background. When scientists study it, they see tiny temperature fluctuations. These fluctuations represent those early density differences. They are incredibly minor, barely a fraction of a percent. Yet those small differences determine the entire layout of the universe we see now. Entire galaxy clusters formed around those slightly denser regions. Entire voids formed around the slightly emptier ones. Inflation didn't just make space enormous, it created the pattern of spacing that everything else followed. As the universe continued cooling, matter began forming into clouds. These clouds were far apart from each other because the initial stretching had placed them that way. Over millions of years, gravity caused these clouds to collapse further, creating stars. Stars formed into clusters, and clusters drifted into loose families. Eventually, these families formed galaxies. But even when galaxies began taking shape, the distances between them were so large that the emptiness between them dominated the scene. This is why galaxies are like islands in a vast ocean. They formed in the only places matter existed in high enough quantities to condense. Everywhere else, there simply wasn't enough material to build anything. This raises an important point. Space is spacious not because matter was removed, but because matter was never evenly placed to begin with. The rapid expansion after the earliest moments prevented anything from settling evenly. When gravity later tried to gather matter into structures, it could only work locally. It had no chance of filling the enormous distances between the seeds left behind. Once expansion had created those gaps, the gaps were permanent. Gravity can gather material within a region, but it cannot reach across billions of light years to fill the voids. The emptiness became part of the universe's architecture right away and has remained that way ever since. Another factor that made space even more spacious over time is the ongoing expansion of the universe. Expansion never stopped. It slowed for a while, but it never reversed. As the universe aged, something unexpected happened. The expansion began accelerating. This acceleration is driven by something called dark energy. Even though we don't fully understand dark energy, we can observe its effects. Galaxies that should have been slowing down in their recession from each other began speeding up instead. The space between them increased more rapidly than gravity could compensate for. This added another layer to the spaciousness. Not only did inflation create the first enormous gaps, but dark energy later increased them. When you combine the effects of early inflation with the later influence of dark energy, the result becomes clear. Space didn't just become spacious, its spaciousness grew continuously. The empty regions expanded faster than the matter-rich regions could fill them. The growing voids became some of the largest structures in the universe, even though they contain almost no material. Cosmic voids often span hundreds of millions of light years across. They aren't completely empty, but the matter inside them is so thinly spread that it barely interrupts light passing through. The emptiness is so pronounced that if you placed a galaxy in the middle of a large void, it would be too far from other galaxies to join any cluster. It would drift alone. Understanding how these vast spaces formed helps explain another interesting fact. Matter is actually rare. If you took all the matter in the universe and compressed it evenly through all of space, the density would be incredibly low. The reason it appears high in certain places is that matter collects due to gravity. Wherever matter gathers, it becomes dense enough to form stars and planets. But these areas are tiny compared to the overall volume. The universe behaves more like a web than a solid structure. Thin filaments of galaxies stretch between enormous empty regions. The empty regions make up most of the volume, while the filaments hold most of the matter. This pattern isn't random. It follows the early quantum fluctuations amplified by inflation. Those variations created a blueprint that gravity followed. Matter falls into the deep valleys and avoids the high regions. If you could see the entire structure at once, it would resemble a network of threads surrounding balloons. The balloons are the voids, the threads are the galaxy clusters. The structure is elegant in a simple physical way. It's the natural outcome of having a universe governed by expansion, gravity, and the early conditions set by inflation. Another way space became spacious involves the speed at which light travels. Light moves fast, but not infinitely fast. That means the observable universe is limited by the distance light has reached since the beginning. The space beyond that boundary exists, but we can't see it yet. As the boundary expands, the volume we can observe grows as well. But the space inside that volume also continues expanding. Over billions of years, this creates a situation where regions once connected drift beyond each other's reach. Space doesn't just grow outward, it grows everywhere at once. This constant growth increases the gaps between things, even if the things themselves stay where they are. It's natural to wonder whether the spaciousness could ever reverse. Could matter someday fill more of the universe? Could gravity overcome the expansion? At the moment, everything we observe suggests that expansion will continue. Dark energy accelerates it, and the acceleration appears to be strong enough that gravity cannot reverse it. Over time, galaxies will move farther apart, the spaciousness will increase even more. But that's something to explore later. For now, the important step is understanding that the universe became spacious the moment inflation began, and that spaciousness has only grown with time. This growth didn't require any dramatic actions from matter. It didn't need collisions or explosions. It happened because space itself can stretch independently of what it contains. Matter rode along with the stretching, but could not keep up evenly. That's why distances grew faster than matter could fill them. The outcome was a universe where emptiness dominates simply because emptiness is easier to create. Matter needs conditions to clump. Emptiness appears whenever those conditions fail. By seeing how space expanded into what it is now, the earlier illusion of fullness becomes easier to let go of. The universe is spacious because it always had more room than matter could occupy. It expanded faster than anything could arrange itself evenly. The emptiness wasn't carved out, it was created from the beginning. And that initial spaciousness kept increasing, shaping everything that came afterward. When you zoom out far enough, the universe looks mostly empty because galaxies and stars occupy only thin stretches of space. But if you zoom in instead of out, the same pattern shows up again. The emptiness is not just a large-scale feature. It's built into the smallest structures you can examine. The more closely you investigate matter, the more you notice that the solidness you feel in everyday life is an interpretation your senses create, not a description of the world's structure. Atoms, the basic units of matter, are not compact objects. They are almost entirely empty inside. They behave as though they have shape and presence. But mechanically they are made from extremely small particles separated by comparatively enormous distances. If you were able to see them directly, the idea of them being tiny islands scattered through a sea of emptiness would not feel like a metaphor. It would feel like an accurate observation. If you take a moment to imagine shrinking down until you could observe a single atom at its own scale, the first surprise would be how little there is to see. Even if you expected something small and compact, the gap between that expectation and the reality would be large. The atom contains a nucleus in its centre, a dense object made from protons and neutrons. That nucleus is incredibly tiny compared to the full size of the atom. Surrounding it are electrons, but not in the way that planets surround a sun. They do not move in predictable orbits like small spheres circling a larger one. They exist as regions of probability, places where they are likely to be found. These regions are large relative to the nucleus. Their presence creates the structure of the atom, but they don't fill that structure. Between the nucleus and these electron regions, there is no substance. It is simply open space. If the nucleus were inflated to the size of a grain of sand, the rest of the atom would extend outward to a sphere that could be meters across. The electrons, which are themselves far smaller, would occupy areas near the outer edges. Everything between that grain of sand and the electron regions would contain nothing. This isn't an exaggeration for effect. Measurements confirm that the nucleus makes up only a tiny fraction of the atom's volume. The rest of the volume contributes no material content. It behaves like space, not like the interior of a solid object. The forces inside the atom give it structure and stability, but those forces operate across emptiness. This emptiness isn't a flaw or a mistake. It's a requirement. Atoms rely on the space inside them to establish the conditions that allow electrons to stay bound but not collapse into the nucleus. Without that interior space, atoms wouldn't behave in ways that support chemistry, bonding, or stability. The gaps allow electrons to exist in energy levels rather than spiraling inward. The emptiness gives atoms the ability to form molecules. If atoms were solid spheres with no interior space, the physical properties of matter would be completely different. Understanding this helps explain why everything you see and touch feels solid, even though the particles that form it are widely separated. The sensation of solidness comes from the electromagnetic forces between the atoms in your body and the atoms in the objects you interact with. When you press your hand onto a surface, your hand doesn't sink through the atoms of the material because the electrons in your skin repel the electrons in the surface. The repulsion is strong enough to prevent overlap. You experience this as resistance. To your senses, that feels like pushing against something that occupies space completely. But at the atomic level, nothing is actually touching in the way most people imagine. The sensation of contact is produced by forces acting across empty distances. If you were to remove all the empty space inside every atom in your body and compress the particles down to their actual volume, your entire mass would shrink to something unimaginably small. The number often used is that the human body, if compressed so that no space existed between its particles, would fit into a cube much smaller than a grain of salt. That small volume would contain all the matter you're made of. Everything else, your height, the space you occupy, the volume of your lungs, the shape of your hands, is formed by the arrangement of atoms separated by vast internal emptiness. The same applies to every solid object. A piece of metal, a stone, a sheet of wood, or a glass of water all owe their structure to the arrangement of atoms rather than the atoms themselves. The space inside each atom and the space between atoms dominates the object's volume. Forces hold them in place. Those forces give the appearance of solidity. But if you could look at the object with enough detail, you would see that it is mostly empty. This pattern extends into molecules. A molecule is simply a set of atoms arranged in a specific configuration. The emptiness inside each atom still exists, and the emptiness between atoms adds even more open volume. Molecules are not continuous or uninterrupted structures. They are clusters held together by electromagnetic interactions. These interactions create bonds strong enough to give molecules stability, but the components don't pack together without leaving gaps. Even in tightly bonded solids, the atoms do not touch. They approach each other to distances where their electron clouds begin interacting, and that interaction is what holds them in place. This spacing creates a kind of lattice in many materials. A lattice looks orderly, with atoms positioned in repeating patterns. But the repeating pattern does not remove the emptiness. It simply arranges the empty and occupied regions into a consistent layout. When you examine the lattice closely, the empty volumes between atoms are enormous relative to the nuclei. The lattice persists because the forces between atoms create balance, not because the atoms pack tightly. The idea that atoms are mostly empty might seem counterintuitive because we instinctively associate matter with solidity. We equate the objects we see with filled volume. But the more carefully you examine matter, the clearer it becomes that emptiness is the majority component at every scale. Even in extremely dense objects like the core of a star, atoms retain significant internal space until the environment becomes extreme enough to break their structure. Only in the most compact objects like neutron stars does the atomic structure collapse entirely, removing internal space. But those conditions don't describe the ordinary universe. Under normal and even extreme conditions, emptiness dominates. Because atoms contain so much empty space, light can pass through large areas of material without being absorbed. When light interacts with matter, it usually interacts with the electrons, not with the spaces between them. The electrons determine how light behaves, whether it reflects, refracts, or passes through. The interior emptiness doesn't interfere with the light at all. This is why transparent materials exist. Glass, for example, doesn't block visible light because its electrons don't absorb photons of those wavelengths. The emptiness inside the atoms plays no active role in blocking or allowing the light. It simply exists as part of the atomic structure. Something similar happens with sound. sound travels through matter by compressing and expanding the material. It does this by moving atoms slightly closer together or slightly farther apart. But even during a compression, the atoms remain separated by large volumes of space. This sound wave moves through the structure created by the arrangement of these emptiness-dominated units. The atoms respond to changes in pressure, but they do so without eliminating their internal or external gaps. Heat also relies on the atomic structure. When an object warms, the atoms vibrate more energetically. They don't fill the space between them. They move within the lattice, pushing against each other through forces rather than through physical contact. The empty spaces remain part of the structure. The atoms simply oscillate within that field. When you consider the emptiness at the atomic scale, it becomes easier to understand why the universe at large contains so much empty space. The structure of matter reflects the structure of the cosmos. In both cases, matter is not a continuous substance. It is a rare component arranged in ways that create form and behaviour. Emptiness is the background that supports the arrangement. It is not a temporary condition. It is fundamental. Once you accept that atoms are mostly empty, and molecules are mostly empty, and objects are mostly empty, the idea that galaxies and clusters are separated by enormous distances feels like a natural extension rather than a contradiction. Atoms also show that emptiness does not imply lack of activity. Inside atoms, forces constantly act across the open spaces. Electrons occupy energy levels and transition between them. The nucleus undergoes interactions that shape the stability of the atom. None of these processes require physical contact. They operate across empty distances. The emptiness does not reduce the atom's complexity or behaviour. It simply provides the spacing necessary for those behaviours to exist. In this way, atomic structure provides an example of how emptiness can support activity rather than hinder it. The emptiness inside atoms also affects how matter responds to pressure. If you compress a material, you reduce the spacing between atoms, but you don't remove the internal emptiness. At normal pressures, the atomic structure remains intact. Only under extreme conditions, such as in the interior of a giant planet, do atoms begin to compress in a way that reduces the internal gaps. Even then, the nucleus remains tiny compared to the electron structure. Complete removal of atomic emptiness happens only when matter is compressed so much that electrons are forced into the nucleus. At that point, atoms no longer exist as atoms. But that environment lies far beyond anything found in familiar settings. Another interesting detail is that the emptiness in atoms doesn't slow down electrical currents. Electricity flows because electrons can move through a material. They move from atom to atom not by physically travelling through filled space, but by transitioning through arrangements of potential. These transitions depend on the structure of the atoms and the forces inside them. The emptiness does not stop the movement. It simply defines the space in which the forces operate. Understanding atomic emptiness also explains why matter cannot occupy the same space. Even though atoms are mostly empty, their electron regions cannot overlap without generating strong repulsive forces. Those forces act across the empty gaps and prevent atoms from collapsing into each other. This maintenance of distance is part of what gives matter volume and shape. It means that matter occupies space even though it is mostly empty internally. The occupied volume comes from the limits created by electron interactions, rather than from the material filling the volume. When you step back and look at the bigger picture, atoms behave like tiny islands surrounded by open regions. They gather into structures where the islands remain separate. The emptiness between them is a stable part of the arrangement. At larger scales, clusters of atoms form objects that retain the same pattern, and at even larger scales, clusters of stars and galaxies follow the same trend. The universe uses emptiness at every level. Matter exists within it, shaped by forces that keep everything arranged, but prevent any area from becoming crowded. This shared structure suggests that emptiness is not a random byproduct. It appears consistently in every scale we examine. The way atoms form, the way galaxies distribute themselves, and the way the universe expands all point to a reality where emptiness plays a central role. The spaces aren't interruptions or errors, they are the natural environment in which matter operates. Recognizing this helps make sense of the idea that the universe is mostly empty. It isn't empty because something is missing. It is empty because that emptiness is part of how everything fits together. When you move away from the scale of atoms and begin drifting outward toward the places where stars live, you might expect the universe to start feeling fuller. Stars give the impression of activity and brightness. They release enormous energy. They form planets, send out light, create heat, and fill the sky with the points we notice when we look up on a clear night. Because of that, it can be easy to assume that stars sit close together, crowding the galaxy with their presence. The view from Earth encourages this thought. The night sky shows hundreds of stars in a single glance, thousands if you go somewhere dark. If you've ever seen the Milky Way stretch overhead, it can feel as though stars are packed tightly across the sky. But this appearance doesn't match the reality. The deeper you go into the actual layout of space, the more you find that stars are separated by enormous distances. Most of the night sky is shaped by silence rather than activity. This silence isn't the kind you hear when a room is quiet. It's a lack of interaction. Stars don't press against each other. They don't drift close enough to disrupt each other. They sit far apart in a way that makes collisions rare events in the entire history of a galaxy. Even inside the densest regions, where new stars are forming in large numbers, the actual spacing between them remains immense. If the space between atoms feels large compared to the particles inside them, the space between stars takes that idea and stretches it far beyond anything that seems intuitive. If you place two stars close enough that their light appears side by side from our perspective, you might imagine that they sit near each other. But in three-dimensional space, they can be separated by light years. A light year is a distance that light itself takes a full year to travel. Light moves at the fastest speed nature allows, yet even at that speed, it requires 12 months to cross the distance between one typical star and the next. For a physical object, the journey would take much longer, and between those stars, nothing occupies the space in the way your senses expect. There are no scattered objects thick enough to notice. There is no continuous medium. There is just a wide region where nothing affects the light passing through. The Sun sits inside one of these regions. Our nearest neighbouring star, Proxima Centauri, is a little more than 4 light-years away. If you could compress that distance down to something understandable, you might imagine the Sun as a large sphere sitting in the centre of a vast, quiet expanse. Proxima Centauri would be another sphere located so far away that you could fit trillions of Earths between them. Everything in between would be empty. The planets that orbit the Sun occupy an extremely small volume compared to this gap. The objects that drift through interstellar space do not fill the emptiness. They are sparse and isolated, spread so thinly that a spacecraft could travel through those regions for decades without encountering anything larger than a grain of dust. Even light takes its time crossing these regions. When you see the starlight in the sky, you're seeing something that travelled through silence for years, sometimes for centuries or even millennia. Nothing stops it. Nothing bends it beyond the slight effects created by gravity. Nothing interacts with it unless it happens to strike a rare particle drifting through the void. This ongoing travel of light reveals how empty the space between stars really is. If there were enough matter to interrupt light, the stars wouldn't appear as sharp points. Their light would scatter. Instead, the light travels nearly undisturbed. The great silence also explains why the night sky remains dark, even though the galaxy contains billions of stars. If stars were close together, their combined light would brighten the entire sky. The darkness between stars, not the presence of stars themselves, creates our experience of night. The stars are far enough apart that each one contributes only a tiny amount of light to your eyes. The rest of the scene is shaped by darkness that comes from the empty space between them. When you imagine the galaxy from above, you might picture its spiral arms filled with stars. Diagrams often show this distribution as a glowing band. But these diagrams simplify the distances. Each point in the diagram stands for a star, but the stars are not sitting next to each other. The distance between them remains vast. Even in areas where star formation is active, the gaps remain enormous compared to the size of the stars themselves. The emptiness inside an atom might seem surprising, but the emptiness between stars makes that earlier scale feel small. To understand how enormous these distances feel in real terms, you can think of the solar system again. The planets orbit the Sun in a relatively thin disk. Within this disk, the spacing between planets is significant but still small enough for our instruments to explore. Beyond the outer planets lies a region filled with icy bodies, but even there, the objects remain sparse. Eventually, you reach the edge of the solar system's influence and enter interstellar space. Once there, the silence becomes almost complete. The only things present are the occasional atom or molecule drifting through a volume that dwarfs everything in our system. This pattern continues throughout the galaxy. Stars are born in groups inside giant clouds. These groups spread out over time, leaving behind regions where only a few stars remain close. Even the clusters that stay bound together do not approach the crowded appearance one might expect from pictures. They contain hundreds or thousands of stars, but those stars occupy such a large volume that the spaces between them remain vast. You could fly a spacecraft through a cluster without hitting anything. The stars would be bright, but they would sit far apart, each surrounded by a large territory of quiet emptiness. The silence doesn't just exist in physical spacing. It exists in the way stars interact. Most stars don't communicate energy directly with one another. Their gravity influences nearby objects, and their light travels outward, but they do not exchange material or exert pressure on each other. They behave independently, shaped mostly by their own processes and by their local environments. The great silence lets them develop without constant interference. One reason stars are so widely separated is that the universe has expanded for billions of years. The early galaxy was denser, but even then, stars weren't close enough to cause frequent collisions. Over time, the galaxy stretched, rotated, and reorganized. Stars moved along their orbits. The space between them increased. The gravitational fields shaped the orbits, but didn't pull the stars together. Instead, the stars followed paths determined by the combined mass of the galaxy, rather than by each other individually. Because of this, the empty regions widened rather than shrinking. The silence between stars also affects the development of solar systems. If stars were closer together, their gravitational influence would disrupt the orbits of planets. Planets need stable conditions to form. They arise from disks of gas and dust that slowly cool and condense around young stars. If another star passed too close, the disk could be disturbed or torn apart. The resulting planets might be flung into space or drawn into new orbits. The large distances protect developing systems. They allow planets to orbit their stars for billions of years without interference from neighbouring stars. The emptiness between stars isn't just a background feature. It is part of the reason solar systems can exist. This spacing also influences the potential for life. Life requires stable environments. Those environments rely on steady orbits and consistent conditions. If stars drifted close together, their gravitational interactions would destabilize these conditions. The emptiness between them protects the environments that life depends on. Even though it might feel counterintuitive, the silence supports the possibility of complexity. Without vast regions of quiet, the universe would be too chaotic for planets to maintain long-term stability. The silence isn't uniform. Some regions contain more stars. The centre of the galaxy has higher density. If you were near the galactic core, the night sky would look brighter. More stars would fill the field of view. But even in those dense regions, stars are still separated by large gaps. You could still travel enormous distances without encountering anything. The environments differ in brightness and gravitational intensity, but not in the fundamental reality that emptiness dominates. This pattern continues in the spaces between galaxies. The gaps become even larger. Galaxies form clusters, and those clusters are separated by spaces so immense that light takes billions of years to cross them. The great silence between stars is the same silence that extends between galaxies. It is the same silence that shapes galaxy clusters and voids. The distances grow, but the pattern remains consistent. Matter clumps. Emptiness expands around it. When thinking about the silence between stars, it's natural to wonder whether these distances could shrink over time. Could stars drift closer? Could regions collide more often? Observation suggests the opposite. The universe continues to expand. Stars do not approach each other unless they belong to a gravitationally bound system. Most stars drift farther apart as the galaxy evolves. The future likely holds even more silence, with distances increasing as the expansion accelerates. This spreading doesn't remove existing structures. It stretches the regions between them. The light from distant stars will travel longer before reaching anywhere. The silence between them will deepen. The stars will remain bright locally, but the background will grow darker as the distances widen. But that quiet is something to explore later. For now, the important point is that the silence between stars is not an isolated feature. It arises naturally when matter is sparse and space is plentiful. Understanding the great silence also highlights how unusual it is that we can see the stars at all. Their light crosses enormous distances without being absorbed by the empty regions. It arrives here after travelling through places where nothing interfered with it. If space weren't so empty, the light wouldn't reach us with such clarity. The silence allows the stars to be visible. It allows us to observe the galaxy's structure. It allows us to know that these huge distances exist. If you imagined yourself drifting between stars, the silence would feel different from the quiet of any place on Earth. There would be no air to carry sound, no surfaces to reflect noise, no vibrations except the ones inside your own spacecraft. The nearest stars would be points of light in the distance. Nothing would move past you. Nothing would obscure the view. You could drift for years without seeing anything change noticeably. The emptiness would not feel active or passive. It would simply be present. As you continue exploring the structure of the universe, the silence becomes a constant companion. It supports the formation and evolution of stars. It keeps their environment stable. It shapes the night sky. It reveals the scale of the cosmos. When you step back far enough from the silence between individual stars, something new begins to appear. The emptiness doesn't vanish, but patterns emerge within it. The stars that look so isolated from up close begin arranging themselves into structures that trace the shape of the universe on a much larger scale. These structures are what we call galaxies. From a distance, a galaxy looks like a swirl of light, a concentrated region that stands out from the surrounding darkness. But the same rules that govern atoms and stars still apply. Even though galaxies look dense when viewed as a whole, they are mostly empty inside. They contain so much space between their components that the overall impression of solidness is another one of those illusions created by distance and perspective. If you've ever looked at pictures of the Milky Way taken from Earth, you've probably noticed the band of light stretching across the sky. It looks like a crowded river of brightness. In some places, the band seems so thick that you might imagine the stars are packed together tightly, almost touching. But those images combine enormous distances into a single view. They compress points of light that sit tens of thousands of light years apart. The brightness you see doesn't result from a lack of space inside the galaxy. It results from the combined light of so many stars overlapping when seen from far away. Imagine standing on one side of a very large city at night, looking toward the distant skyline. The lights in the buildings appear close together because you see them as a group. But if you were to travel into the city, you would find streets, parks, and open spaces that separate those illuminated windows. Galaxies behave in a similar way. The stars only look crowded when viewed from afar. Up close, the emptiness remains dominant. The scale changes, but the structure follows the same pattern as the regions between stars. The Milky Way, the galaxy that contains our Sun, is enormous. It stretches about 100,000 light-years from one edge to the other. If you could travel across it in a straight line, even at extremely high speeds, the journey would span billions of lifetimes. And yet, for all its size, the galaxy doesn't contain enough stars to fill it in any dense way. The Sun is one of hundreds of billions of stars, but those stars are spread through such a large volume that the average distance between any two is still several light-years. That gap is so large that most of the galaxy consists of open regions where nothing occupies the space. The visible structure of the Milky Way includes spiral arms filled with stars, gas and dust. These arms wind outward from a central bulge that contains older stars. The spiral arms aren't solid bands, they are patterns of density, regions where material is slightly more compressed than in the surrounding areas. They function a little like slow-moving waves in a crowd. As stars orbit the centre of the galaxy, they move in and out of these denser regions, creating the appearance of a continuous shape, even though the stars themselves come and go. This pattern makes galaxies appear like swirls when viewed from above, but the swirls don't contain a continuous layer of light. They are shaped by billions of small points separated by wide distances. If you were floating inside one of these arms, you wouldn't see a glowing ribbon. You would see stars scattered across the sky the same way you do from Earth. It would not look like a solid shape surrounding you. The structure becomes visible only when viewed from a distance that allows the combined light to form a pattern. Galaxies come in different shapes. Some are spirals like our own. Others are elliptical, forming large, smooth, elongated clusters without distinct arms. Some are irregular, lacking a clear form. But regardless of their shape, the same principle applies. The stars inside them occupy only a tiny fraction of the space. The gaps between stars dwarf the stars themselves. Even in the densest regions, like the centre of the galaxy, the spacing remains large enough that stars rarely interact closely. In the central bulge of the Milky Way, stars appear more crowded. The density is higher. But even there, if you could travel through the region, you wouldn't find a continuous wall of light. You would still encounter large stretches of empty space. The stars might be closer compared to the outer regions, but the distances are still enormous. The fact that the Milky Way contains hundreds of billions of stars might sound like a huge number. But when spread across a volume of this size, the result is a structure filled with more emptiness than matter. These large distances explain why galaxies are stable over long periods. If stars sat closer together, their gravity would disrupt each other's orbits. The galaxy would not be able to maintain a consistent shape. Instead, the wide spacing allows stars to move along their paths without frequent interference. The rotation of the galaxy takes hundreds of millions of years, and the stars follow smooth, predictable orbits. The emptiness between them provides enough room for these orbits to remain uninterrupted. Another important detail is that galaxies contain more than just stars. They include gas, dust, and dark matter. The gas and dust form large clouds where new stars can emerge. But even these clouds are mostly empty compared to the volumes they occupy. The particles inside them are spread thinly. A cloud might be large enough to span dozens of light years, yet the density inside it could be lower than the air inside a room. Only when gravity compresses parts of the cloud does it become dense enough to form new stars. Dark matter, which we can't see directly, surrounds galaxies in large halos. Even though we can't observe dark matter visually, its gravitational effects help hold galaxies together. Otherwise, the visible matter alone wouldn't generate enough gravity to prevent galaxies from flying apart as they rotate. The presence of dark matter doesn't fill the voids with substance. It only adds gravitational influence. The emptiness remains open and unobstructed. The presence of these additional components shows that galaxies are dynamic. They evolve over time, forming new stars while older ones fade. But through all this activity, the emptiness remains the fundamental backdrop. It gives the stars room to move through their orbits. It gives gas clouds room to drift and collapse. It gives the galaxy space to change without collapsing into a single mass. Another striking feature is that galaxies themselves exist in isolation. They drift through even larger regions of emptiness that separate them from other galaxies. The Milky Way has a few neighbouring galaxies, including the Andromeda Galaxy and the smaller satellites that orbit around it. But the distances between major galaxies are immense. Andromeda, for example, is more than 2 million light-years away. Even though it's heading toward the Milky Way and will eventually merge with it, that movement takes place over billions of years. The emptiness between them is so vast that the two galaxies can approach each other without altering their internal structures for a long time. When galaxies do interact, such as during mergers, the individual stars still almost never collide. Even when two galaxies pass through each other, the stars slip past one another because the spaces between them are so large. Mergers reshape galaxies through gravitational forces rather than through physical collisions between stars. The emptiness makes these interactions less destructive than they might seem. The large-scale shapes shift and blend, but the stars mostly retain their integrity. The light from galaxies travels enormous distances before it reaches us. When telescopes observe galaxies billions of light-years away, they are seeing light that left those galaxies long before Earth even formed. The light crosses areas so empty that nothing blocks its path. This allows astronomers to observe structures far beyond what the naked eye can see. The clarity of these distant images is a reminder of just how unoccupied the universe is. If anything filled the emptiness between galaxies, the light would scatter or blur long before reaching our telescopes. Inside the Milky Way, the layout of stars and gas creates the structure we associate with spiral arms. But the arms are not rigid. They rotate slowly relative to the stars themselves. The stars move in and out of the arms as they orbit. The arms appear because they are areas where stars are slightly more likely to form and gather. But these areas aren't continuous or dense. They are shaped by subtle differences in gravitational forces. The stars inside them come and go, but the pattern persists. The galaxy also contains large regions of dust that block starlight. These dust clouds create dark lanes when photographed. These lanes aren't solid walls. They are concentrations of particles spread over large distances. They block enough light to create the appearance of solid shapes, but they remain mostly empty spaces structurally. You could travel through these dust regions without encountering anything that feels like a barrier. The Milky Way's structure also includes a disk, a halo, and extended streams of stars created by past mergers with smaller galaxies. These features show that galaxies are not static. They change continually. But they all share the same underlying nature: small concentrations of matter, separated by large regions of emptiness. The visual complexity of a galaxy results from these distributed components moving in patterns shaped by gravity. Understanding galaxies as islands of matter spread through the cosmic ocean shows that the emptiness we see between stars extends far beyond individual solar systems. It defines the structure of the entire galaxy, and when you zoom out even farther, you discover that the distribution of galaxies follows similar patterns on a larger scale. They gather into clusters and superclusters, and those clusters sit along filaments that outline the largest structures in the universe. But between them lie even larger voids, regions of almost complete emptiness. These voids form the majority of the universe's volume. The contrast between the bright swirls of galaxies and the vast darkness between them highlights a consistent theme. Everything we observe, from atoms to stars to galaxies, uses emptiness as the primary element of structure. Matter collects where gravity allows it, and everything else remains open space. The swirls of light inside galaxies are the visible traces of matter condensed enough to produce energy. The darkness between them reveals how much of the universe lies untouched by this condensation. When you look at a galaxy from far away, it appears to be a neatly contained island of stars drifting through space. The bright bands, the glowing arms, the calm rotation all give the impression of a well-organised structure that stays intact because of the matter you can see. But if you try to understand why galaxies hold together, something doesn't add up. The stars inside them move in ways that don't match the amount of visible material. If the stars behaved according to only the matter we can detect directly, the galaxies should fall apart. Their rotation would fling stars outward. The outer regions of galaxies should drift away over time, but they don't. Something holds them in place. Something that generates more gravity than the visible matter accounts for. That something is what we call dark matter, and it plays a central role in determining how spacious the universe becomes and how matter arranges itself into the patterns we observe. Dark matter isn't a substance we can see or detect with traditional instruments. It doesn't reflect light or absorb it. It doesn't produce energy the way stars do. We know it exists because of its gravitational effects. When scientists measured the speeds at which stars orbit inside galaxies, the results didn't match predictions. The outer stars move just as quickly as the ones closer to the centre. That shouldn't happen if only visible matter were influencing their motion. The distances involved are so large that the gravitational pull from the centre shouldn't be strong enough to maintain high speeds at the edges. Yet the edges don't drift away. They remain part of the galaxy. This tells us that something unseen generates additional gravity, shaping the movement of stars. The presence of dark matter becomes clearer when you compare galaxies to rings of planets, or moons around a planet. In our solar system, the planets closest to the Sun move the fastest. Mercury moves quickly, Venus moves more slowly, Earth slower still. Each planet's speed matches the gravitational influence of the Sun and its distance from it. That pattern doesn't occur in galaxies. Instead, stars near the outer regions move at speeds that suggest there is far more mass in the galaxy than we can see. That mass doesn't shine. It doesn't interact with light. But it might be 5 or 6 times more abundant than ordinary matter. If you could see a galaxy with dark matter visible, it would not look like a thin disk with a central bulge. It would be enclosed inside a large rounded halo extending far beyond the stars. The visible galaxy would sit inside this invisible structure, held in place by its gravity. That halo contains most of the galaxy's mass, even though we can't detect it directly. The stars, gas and dust are only a small fraction of the total. Dark matter also influences the arrangement of galaxies on larger scales. When scientists map the universe, they find that galaxies aren't evenly spread out. They gather along enormous structures that span hundreds of millions of light years. These structures look like threads or walls outlining regions with almost no galaxies at all. The empty regions, called voids, dominate much of the universe. The filaments between them form a kind of scaffold. Galaxies sit along these filaments and cluster at their intersections. That scaffold is shaped by dark matter. The invisible material gathered first, forming dense regions where gravity was stronger. Ordinary matter fell into these regions, forming galaxies and clusters. This means that the distribution of galaxies isn't random. It follows the pattern created by dark matter. The visible universe looks the way it does because the invisible universe formed its layout first. If you think of it in terms of cause and effect, dark matter created the highways and intersections, and galaxies followed the roads. But unlike physical roads, these structures don't consist of solid shapes. They are arrangements of gravity created by matter that emits no light. When dark matter gathered in the early universe, it created regions where gravity was strong enough for ordinary matter to condense into stars. But dark matter itself didn't clump into tight structures the way ordinary matter does. It spread into large halos around galaxies, influencing their behaviour without collapsing inward. These halos extend far into the empty regions around galaxies, providing the gravitational glue that keeps their stars bound. The halos aren't uniform. Their density changes, forming areas slightly stronger or weaker in gravitational influence. When multiple halos interact, they create larger gravitational wells that attract more matter. These interactions form the bridges between galaxies. The bridges aren't visible, but they influence how galaxies move. They keep clusters bound together. They guide the motion of entire groups of galaxies across vast distances. These invisible bridges don't behave like solid beams. They don't have edges or surfaces. They are regions where gravity blends from one halo into another. If you travelled through one of these regions, you wouldn't see anything different. There would be no change in the surrounding emptiness, but your path would still follow the slight curve created by the gravitational pull. Galaxies do the same. They follow these curves not because they choose to, but because gravity shapes their paths. One of the most striking things about dark matter's influence is how subtle it is. You can't point to a specific feature in the sky and say, "This is dark matter." You detect it by noticing how objects move. When the light from distant galaxies bends in ways that can't be explained by visible mass, dark matter provides the explanation. The bending happens because the gravity created by dark matter changes the path of light. This process, called gravitational lensing, helps map the invisible structures. Even though dark matter doesn't interact with light directly, its gravitational effects change how light travels. These effects reveal that dark matter forms a kind of backbone for the universe. Without it, galaxies wouldn't be able to remain intact. The large-scale structure of the universe wouldn't exist in its current form. The voids would be smaller, and the galaxy clusters wouldn't have the same shape. Dark matter doesn't fill the emptiness, it shapes it. It influences the distribution of ordinary matter without occupying the space in a visible way. The empty regions between galaxies are shaped by these invisible forces. Dark matter forms concentrated regions where galaxies cluster, leaving the surrounding areas sparse. The emptiness grows around these structures, creating vast spaces where almost no matter resides. Because dark matter doesn't collapse into stars, it doesn't produce light. It contributes to the emptiness by providing gravity without creating visible objects. As a result, the universe becomes even more dominated by darkness, not just because stars are far apart, but because the material that holds them in place doesn't emit any light at all. One way to picture dark matter's role is to imagine observing the motion of a group of galaxies without knowing what causes their movement. You would notice that they orbit each other in ways that shouldn't be possible if only visible matter were present. They move too quickly. The cluster should disperse if based on visible mass alone. The fact that it doesn't disperse tells you that something else is generating the gravity to hold it together. Dark matter doesn't drift outward under the influence of expansion the way ordinary matter does. It forms stable regions that anchor galaxies in place. It's important to recognize that dark matter doesn't behave like the matter we interact with every day. It doesn't collide with ordinary matter. It doesn't form atoms or molecules. It doesn't emit heat or light. These differences explain why it spreads through space in large, diffuse regions rather than compacting into stars. The only force it interacts with is gravity. That simplicity gives it a unique role in shaping the cosmos. It gathers into vast halos but doesn't form smaller structures. Its distribution remains smoother and more extended than ordinary matter. It doesn't fragment or ignite. It remains invisible but influential. Dark matter also influences how galaxies move through space. When galaxies form inside dark matter halos, they inherit the motion of the halo itself. The halos drift through the universe along the gravitational landscape formed by other halos. The galaxies follow these paths. Over billions of years, this movement creates patterns of flows where galaxies drift toward regions with larger concentrations of dark matter. These patterns aren't visible, but they affect the arrangement of galaxies into clusters and superclusters. The invisible bridges formed by dark matter create long-range connections between galaxies. These connections keep clusters bound even across enormous distances. In some regions, the bridges extend so far that they are difficult to map. They influence the motion of galaxies beyond what visible matter can explain. This influence doesn't create physical links. It creates gravitational pathways that guide motion in subtle but persistent ways. Because dark matter doesn't emit or absorb light, the regions where it dominates appear completely empty. If you were floating through such a region, nothing would reveal its presence. The gravity would be there, but you wouldn't see any difference in the surrounding darkness. You would move along whatever path the gravity allowed, but the emptiness would feel no different from any other part of space. When scientists study the cosmic web, the large-scale pattern of galaxies, they often simulate it by including dark matter. Without dark matter, the simulated universe doesn't match observations. The galaxies spread out too evenly. They don't form filaments or clusters. They don't create the large voids. When dark matter is included, the simulations begin matching the actual universe. The galaxies arrange themselves along the invisible scaffold formed by the dark matter. The voids open up between them. The clusters become dense. The universe gains structure. These simulations help reveal how the early universe evolved. In the beginning, dark matter gathered first. It didn't collapse into dense structures the way ordinary matter does, but it formed regions where gravity was stronger. Ordinary matter followed, cooling and forming stars only within the regions defined by dark matter. As the universe expanded, dark matter structures grew into larger halos. Ordinary matter continued collecting into galaxies within these halos. The resulting pattern formed a network of connections across space. Because dark matter doesn't interact with light, it allows the universe to remain spacious. If dark matter radiated energy, or collided with itself the way ordinary matter does, it might form compact structures. These structures might reduce the emptiness, but dark matter's quiet nature lets it spread into extended regions. The emptiness between galaxies remains open because dark matter doesn't collapse inward. Its role is to shape gravity rather than to fill volume. This invisible framework also influences how the universe's expansion affects galaxies. As space expands, distant galaxies move away from each other. Dark matter halos resist this movement within clusters, keeping galaxies bound. But on larger scales, the expansion stretches the space between clusters. The bridges formed by dark matter contribute to these transitions. They maintain local connections even while the larger universe expands. The emptiness grows, but the structure persists. The presence of dark matter becomes even more interesting when combined with dark energy, which accelerates the expansion of the universe. Together, these two unseen components determine how space evolves. Dark matter shapes where galaxies gather. Dark energy shapes how fast the emptiness grows. They influence each other in ways that determine the future arrangement of the cosmos. Dark matter doesn't shrink the emptiness. It organizes it. It creates the boundaries and connections that define where galaxies can form and how they can move. The emptiness grows around these structures. The universe becomes a balance between visible matter, invisible matter, and expanding space. The great silence that separates stars and galaxies remains, because these components behave differently. Dark matter anchors structures while dark energy pushes them apart. When you reach the point where the influence of dark matter becomes clear, the next question that naturally comes up is why the emptiness between galaxies keeps increasing. Dark matter explains how galaxies hold together and how large-scale structures maintain their shapes, but it doesn't explain why these structures continue drifting farther apart over time. To understand that part of the universe, you need to look at something even more elusive. Dark matter adds gravity, keeping things connected. But something else acts in a way that seems to push space itself outward. That something is what we call dark energy, and its influence determines how large the empty regions of the universe become. Dark energy isn't a substance you can see or collect. It's not a material that forms particles or clouds. It doesn't behave like matter, dark or otherwise. It appears in the equations that describe the expansion of the universe. When scientists observed distant galaxies, they found that the expansion of the universe wasn't slowing down as they had expected. Instead, it was speeding up. This was surprising because gravity should cause expansion to slow with time. If galaxies attract each other through gravity, the expansion should lose momentum. But the observations showed the opposite. The galaxies aren't just moving away from each other, they're doing so faster and faster. This acceleration suggests that space itself has a kind of energy that increases the rate of expansion. That energy doesn't dilute as the universe grows. It has a consistent effect everywhere. As space expands, the amount of dark energy in any given volume remains constant. This characteristic makes dark energy unlike anything else in the universe. The more space expands, the more dark energy influences the expansion. This creates a feedback loop where the growth of space leads to even more growth. The presence of dark energy was inferred by looking at supernovae in distant galaxies. These supernovae act as standard candles because their brightness can be predicted based on their type. When scientists measured how bright these supernovae appeared, they could estimate how far away they were. The distance measurements didn't match the expected slowing of expansion. Instead, they showed acceleration. This discovery required a shift in how we think about the universe. It meant that the emptiness between galaxies wasn't just expanding. The rate of expansion was increasing. Because dark energy works on empty space itself, it doesn't behave like a traditional force. It doesn't push galaxies away from each other the way one object pushes another. It changes the geometry of space so that distances increase even if galaxies are not moving through space in the usual sense. The expansion isn't motion through a background. It is the stretching of the background. This stretching carries galaxies along with it, making the spaces between them larger without requiring any additional movement on their part. The effects of dark energy are not noticeable on small scales. It does not affect the motion of stars inside galaxies. It does not influence the motion of planets around stars. These systems are held together by gravity strong enough to counter the expansion. Dark energy becomes relevant only on very large scales, where the gravitational pull between objects becomes weak compared to the energy that drives expansion. This is why galaxies inside clusters remain bound, while clusters themselves drift apart over time. When you look at the patterns created by dark matter, you see a network of structures where galaxies gather, but dark energy stretches the spaces between these structures. It doesn't pull them apart directly. It increases the separation by expanding the space between them. Over time, this expansion makes the universe more dominated by emptiness. The galaxies stay intact, but the regions around them become broader. It's important to understand that dark energy doesn't act like something inserted into the universe at a particular moment. It has been present throughout the universe's history, but its influence became significant only when the density of matter decreased enough for dark energy to dominate. In the early universe, matter and radiation were much denser. Gravity outweighed the influence of dark energy, but as the universe expanded, matter spread out. The density of matter decreased, while the density of dark energy remained constant. Eventually, dark energy overtook matter in its influence on the expansion. This shift occurred several billion years ago. Before that time, the expansion slowed as gravity acted to pull matter together. After dark energy became dominant, the expansion began accelerating. This transition changed the future shape of the universe. Instead of slowing and potentially reversing, the expansion will continue indefinitely. The emptiness will grow at an increasing rate. As space expands, it creates new regions where galaxies drift beyond each other's gravitational influence. Once that happens, the galaxies can't return to their earlier positions. They become part of a growing field of isolated islands, each surrounded by vast expanses of emptiness. This process doesn't disturb the internal structures of galaxies or clusters, but it increases the distances between them in ways that make the universe feel more dispersed with time. The effect can be seen in the way the observable universe changes. Light takes time to travel. As objects move farther away due to the accelerated expansion, the light they emit takes longer to reach us. Eventually, some galaxies will move so far away that their light will never reach us, even if we wait indefinitely. The expansion of space stretches the light waves until they become too long to detect. These galaxies won't disappear physically, but they will fade from view. The observable universe will shrink in terms of the number of galaxies we can see. This ongoing process means the universe becomes more dominated by emptiness, not just in physical terms, but also in observational terms. Future observers, billions of years from now, will see far fewer galaxies than we see today. Their night skies will be darker, not because stars have vanished, but because the expansion has carried distant galaxies beyond their observable horizon. The emptiness grows in a way that changes what can be known about the universe, as well as what exists within it. The expansion caused by dark energy raises questions about the ultimate fate of the cosmos. If the expansion continues to accelerate, galaxies will drift farther apart indefinitely. The space between them will grow so large that interactions between distant clusters will become impossible. Eventually, even the nearest galaxies will be isolated. Stars inside galaxies will continue to burn, but the galaxies themselves will remain surrounded by enormous stretches of empty space that deepen as time passes. Inside each galaxy, the local structure remains stable, because gravity outweighs dark energy on those scales. But the regions outside those gravitational boundaries become more spacious. The empty spaces between galaxy clusters expand faster than the matter inside them can counter. The clusters become the only dense regions left in an increasingly empty universe. This tension between local stability and large-scale expansion creates a picture of the universe that is both structured and dominated by emptiness. Matter gathers into galaxies and clusters, but the space around them expands steadily. The clusters drift away from each other, creating isolated pockets of matter separated by growing stretches of quiet emptiness. Some theories suggest that dark energy might not remain constant forever. It could change in strength. It could follow an unknown rule that alters its influence over time. If it strengthens, the expansion will accelerate more rapidly. If it weakens, the expansion could slow. But current observations indicate that dark energy behaves consistently across time and space. Its uniform influence makes it one of the most stable components of the cosmos, even though it remains one of the least understood. One of the challenges in understanding dark energy lies in the fact that it doesn't interact with matter or radiation directly. It doesn't form particles or waves. It doesn't produce detectable signals. It exists only through its influence on the geometry of space. Because of this, studying dark energy means studying the expansion of the universe, measuring how galaxies move, how light travels through space, and how structures evolve over time provides clues about dark energy's nature. But despite these clues, the true identity of dark energy remains unknown. Some scientists propose that dark energy is a property of space itself. Others suggest it might be related to fields that fill the universe. Some theories involve modifications to gravity that produce the same effect without requiring a separate energy component. These ideas help frame the discussion, but none have been proven. Dark energy remains a placeholder for an observation, not a complete explanation. Even without knowing what dark energy is, you can understand how it affects the structure of the universe. It increases the emptiness between galaxies and clusters. It creates a future where isolation becomes more common. It determines how the cosmic web evolves. The filaments of galaxies remain connected locally, but the space between them expands faster than those connections can stretch. This expansion affects how matter moves on very large scales. Dark matter forms the scaffolding. Ordinary matter fills the densest regions. Dark energy stretches everything between those regions. The result is a universe where the contrast between something and emptiness becomes more pronounced with time. Galaxies retain their shapes. Stars continue to burn. But the empty spaces expand, becoming the dominant feature of the cosmos. The influence of dark energy also affects how we interpret the past. When you look at distant galaxies, you see them as they were billions of years ago. You see a universe where galaxies were closer together, where the cosmic web was more compact and where the influence of dark energy had not yet dominated. The light reaching you now shows a time before the accelerated expansion took over. As you compare this with the present, the transition becomes clear. The universe has grown more spacious, the emptiness has increased, and that increase continues. Understanding dark energy means accepting that the universe changes not just because matter moves, but because space itself evolves. The fabric of the universe expands, creating new distances. These distances aren't the result of motion through space. They are the result of space growing between objects. This growth doesn't create new matter, it creates new emptiness. The emptiness becomes the defining feature of the universe's future. When you reach the point where dark energy's widening influence becomes clear, the next question often becomes how anything retains structure at all. If space continues to stretch and the distances increase, then something must counterbalance this process in certain regions. That counterbalance is gravity, which remains one of the most important shaping tools of the universe. Gravity doesn't stop the expansion on large scales, but it governs how matter organizes itself locally. It acts in a way that preserves structure even while the surrounding space grows more spacious. This creates an arrangement where matter gathers into concentrated areas, while the emptiness around those areas expands. Understanding this pattern requires looking closely at how gravity operates in the presence of so much space. Gravity doesn't act suddenly. It works slowly, steadily, and without producing any visible effect on its own. You don't see gravity pulling on a distant star. You don't see the curve it creates in space. You understand it through motion. Objects move in paths defined by gravity, and these paths reveal how the invisible shaping occurs. When you look at the large-scale structures of the universe, you can see how gravity has spent billions of years creating patterns that remain stable even as the expansion accelerates. The regions that contain galaxies, clusters, and filaments are held together by gravity strong enough to resist the outward stretching of space. The emptiness between them grows, but the structures remain intact because the gravitational attraction inside them outweighs the changes in space around them. This balance explains why galaxies remain bound in clusters, while the clusters drift away from each other. Inside a cluster, gravity is strong enough to keep galaxies from escaping. The cluster acts as a single large system. But the attraction between different clusters is too weak to overcome the expansion of the universe. As a result, clusters become isolated over time. The emptiness between them widens. But inside each cluster, gravity maintains order, guiding the motion of galaxies and shaping the surrounding space. Gravity's influence also explains why matter collects into specific regions rather than distributing evenly. Long before galaxies existed, matter in the early universe began gathering into slightly denser areas as gravity pulled on the small fluctuations left from the earlier stages of cosmic history. These small fluctuations grew gradually, forming the seeds from which galaxies and clusters would eventually emerge. Gravity amplified these differences over time. Regions that were slightly denser attracted more matter. Regions that were slightly less dense lost material to their neighbours. This process created a pattern where matter formed distinct structures surrounded by empty regions. The areas that lost matter expanded into voids. These voids grew larger as gravity continued pulling matter toward the denser areas. Void regions didn't fill with anything. They became the quiet spaces between structures. Over time, the contrast between dense regions and empty regions increased. Gravity shaped the dense regions, while the expansion of space shaped the empty ones. The universe became a combination of clustered matter and large voids connecting those clusters. One interesting aspect of this process is that gravity doesn't push matter into specific shapes. It influences motion rather than forming structures directly. The shapes arise naturally from the way matter responds to gravitational attraction. In regions with more matter, gravity strengthens. Objects drift inward along curved paths, As they move toward the center of these regions, their combined motion creates the structure. Gravity doesn't carve out the voids directly. It draws matter away from the emptier regions, leaving behind open space that expands with the universe. The result is a pattern where matter gathers into clusters, superclusters, and filaments, while the voids expand around them. These voids can reach hundreds of millions of light-years in diameter. They aren't perfect spheres. They stretch and twist as the surrounding structure evolves. But no matter their shape, they share the same fundamental trait. They contain almost no matter. The few galaxies inside them are spread so thinly that the void seems nearly empty. Gravity also shapes the edges of voids. Where voids meet the denser regions, gravity pulls matter inward. This creates a boundary where matter collects more densely. Galaxies form along these boundaries. Clusters gather at the intersections of filaments. The voids themselves remain open, defined by the absence of matter rather than by any structure they contain. This boundary is not sharp. It's gradual. The density increases slowly as you move from the center of a void toward the surrounding filaments. On smaller scales, gravity shapes stars, planets, and compact objects. On larger scales, gravity shapes clusters and superclusters. But at intermediate scales, gravity plays a calm but persistent role in maintaining the structure of the cosmic web. This web is the arrangement of matter throughout the universe. It consists of long filaments of galaxies connecting massive clusters. These filaments are not solid structures. They're regions where matter gathers more densely. Gravity holds them together through the combined pull of all the galaxies inside them. The cosmic web exists because gravity guided matter over billions of years. Without that guidance, the universe would have become more uniform. The emptiness would still dominate, but the matter would not have formed the patterns we see. Instead, matter would be distributed more evenly, preventing the formation of galaxies and stars. The web-like structure depends on the unevenness created in the early universe, and on gravity's ability to build on those uneven areas. The quiet shaping continues today. Gravity still draws matter inward, strengthening the existing structures even as expansion carries them apart on larger scales. Another important aspect of gravity's influence is how it interacts with dark matter. Dark matter forms the majority of mass in the universe. It doesn't interact with light or ordinary matter except through gravity. This means it plays a major role in shaping the cosmic voids. Dark matter collects in large halos around galaxies and clusters. It also forms extended structures between these halos. The visible matter aligns with these structures because gravity draws it into the same regions. Where dark matter is denser, gravity is stronger. Ordinary matter falls into those regions. Stars form. Galaxies emerge. Where dark matter is sparse, gravity is weaker. Matter doesn't gather there. Over time, those regions become the voids. The invisible side of the universe plays a key role in determining where the empty regions form. Dark matter shapes the structure even though it remains entirely unseen. Gravity's quiet influence continues to guide the motion of galaxies inside clusters. These galaxies orbit around a center determined by the combined mass of the cluster, including the dark matter. Their orbits can be slow or fast depending on distance. They follow paths that reveal the cluster's shape. Because gravity is the dominant force on these scales, the cluster remains bound even as the universe expands around it. The space between clusters may grow, but the cluster itself holds together. As the universe ages, gravity also influences how stars within galaxies form and evolve. In the dense regions where gas clouds gather, gravity causes them to collapse. The collapse is slow at first. It accelerates as the cloud becomes denser. Eventually, the center of the cloud becomes hot enough for nuclear fusion to begin. A star is born. Gravity shapes the cloud into a structure where fusion can occur. Even after the star forms, gravity keeps it stable. The pressure from fusion pushes outward, but gravity pulls inward, maintaining a balance. At the end of a star's life, gravity can cause dramatic changes. When a star runs out of fuel, the balance breaks. If the star is massive enough, gravity pulls the core inward rapidly. The collapse can lead to a supernova. It can create a neutron star. It can form a black hole. Each of these outcomes shows gravity acting on matter in extreme conditions. But even in these cases, gravity doesn't act loudly. It shapes the outcome through motion and collapse rather than through any direct visible force. On the scale of galaxies, gravity organizes matter into spiral arms, central bulges, and extended halos. The stars move along curved paths determined by gravity. Their motion creates the appearance of structure. The arms of spiral galaxies are not solid. They are patterns created by stars moving through regions where density is slightly higher. Gravity maintains these patterns by guiding stars along predictable orbits. The galaxies continue rotating for billions of years because gravity maintains their coherence. The quiet shaping continues in galaxy clusters. Clusters contain hundreds or thousands of galaxies. They also contain hot gas and large amounts of dark matter. The galaxies orbit the centre of the cluster. Their motion reflects the mass of the entire system. The cluster's gravitational field keeps the galaxies bound even when they move at high speeds. Without enough mass, the galaxies would escape. Their motion shows that the cluster contains far more dark matter than visible matter. Gravity ties the entire system together. When clusters interact, gravity reshapes them. Clusters can pass through each other without merging immediately. The galaxies continue their orbits. Their dark matter halos blend and eventually settle into new configurations. The gas inside them can collide and heat up, but the galaxies themselves rarely collide because the space between them is so large. Gravity shapes the long-term evolution of clusters through motion rather than through direct contact. As clusters drift through space, the expansion driven by dark energy increases the distances between them. Gravity counters this only on local scales. The clusters remain bound, but the larger structures separate. This process doesn't eliminate gravity's role. It simply defines the range where gravity remains effective. Inside clusters, gravity dominates. Between clusters, dark energy dominates. This creates a universe where matter is organized into isolated islands surrounded by growing emptiness. The voids themselves continue to expand. Gravity doesn't pull matter into them because there isn't enough matter to reverse the expansion locally. The voids grow as the surrounding clusters move apart. They remain some of the largest features in the universe. Their shapes reflect the distribution of dark matter and the expansion of space. Gravity shapes their boundaries, but the emptiness inside them expands freely. Even though the voids widen, they are not static. They evolve as the surrounding structures move. Some voids merge, some stretch, some remain stable for long periods. But through all of this, gravity continues shaping the arrangement of matter around them. It defines the boundaries. It maintains the structure of the filaments and clusters. The voids exist because matter gathers elsewhere, and that gathering is driven by gravity. When you consider gravity's influence on every scale, from atoms to stars to galaxies to clusters, it becomes clear that the emptiness of the universe isn't a sign of a lack of activity. It is the result of activity. Gravity draws matter into dense regions. Those regions become the sites of complex structures. The regions between them become empty because the matter moved elsewhere. The emptiness is shaped through the absence of matter, not through any direct action. Gravity causes the absence by drawing matter toward the places where structure forms. This ongoing shaping continues as the universe evolves. Matter still falls into existing structures. Voids still expand. The cosmic web becomes more defined. Dark energy increases the distances between clusters. Gravity maintains the coherence within clusters. The combined result is a universe where emptiness grows, structure persists, and the contrast between matter and space becomes more pronounced. When you reach the point where gravity's role becomes clear, something about the universe's overall structure takes on a different clarity. Gravity pulls matter inward. forming clusters, filaments, and superclusters. But as those structures grow, the regions between them naturally become the places where matter does not gather. These spaces evolve into some of the largest features in the universe. They are called cosmic voids, and understanding them helps explain why the universe appears overwhelmingly empty no matter which scale you examine. These voids are not small gaps or scattered vacancies. They are vast territories where galaxies are sparse and matter density falls far below the cosmic average. When scientists map the universe, the voids stand out immediately. They appear as large, roughly spherical or elongated regions that contain very few galaxies. They are surrounded by the filaments and clusters that define the cosmic web. The landscapes created by these contrasts form a structure far larger than any galaxy, cluster, or supercluster. The voids dominate the map not because they contain anything, but because they contain so little. The space inside them is almost pure emptiness. A few galaxies drift inside, but the number is so small compared to the surrounding filaments that the void feels nearly hollow, even when measured across hundreds of millions of light years. These voids form because matter moves away from them. In the early universe, small fluctuations in density caused matter to collect in certain regions. The regions with slightly more mass attracted additional matter. The regions with slightly less mass lost matter as it flowed toward the denser areas. Over time, this process deepened the contrast. The dense regions became the sites of galaxy formation. The less dense regions emptied further, eventually becoming the voids we see today. Gravity shaped this movement, but the expansion of space helped amplify it. As the universe expanded, the empty regions expanded with it. The matter had no reason to flow back once it had moved outward. A cosmic void is not a perfect sphere or a smooth shape. It contains small fluctuations, faint galaxies, and minor structures. But compared to the surrounding regions, its density is extremely low. A typical void might have only 10 to 20% of the average matter density of the universe. The larger voids often drop below that, approaching near vacuum conditions where galaxies are rare enough to appear isolated. These galaxies often have unique properties because their environments differ significantly from those in denser regions. Their evolution takes place without the influences that shape galaxies located in clusters or filaments. The size of these voids varies. Some span tens of millions of light years. Others exceed 100 million. The largest known voids stretch for more than 1 billion light years. These enormous gaps are not empty in the sense that nothing exists within them, but the matter they contain is spread so thinly that it offers almost no gravitational resistance to the expansion around it. The voids grow larger over time because they contain little mass. Gravity cannot gather enough material inside them to alter their expansion. As a result, the voids become some of the fastest growing regions in the universe. If you imagine drifting into a cosmic void and viewing its surroundings, the experience would feel different from anything imaginable on Earth. You would see only a few galaxies scattered across an expanse that feels overwhelmingly still. Their light would appear faint because of the large distances between them. You would not encounter clusters of stars or bright concentrations of matter. You would drift through regions where nothing interrupts your motion, except the occasional gravitational influence of a distant galaxy. The space inside a void lacks the busy structure found in filaments and clusters. This difference exists because the void is the outcome of billions of years of gravitational sorting, where matter has been drawn toward the denser regions and away from the empty ones. The expansion of the universe also affects voids differently than it affects clusters. In clusters, gravity holds matter together tightly enough to resist expansion. In voids, almost no gravity exists to counter the stretching of space. This means voids widen more quickly than any other region of the universe. They are the areas where dark energy's influence becomes most apparent. The emptiness inside them magnifies the effect of the expansion. The galaxies inside them drift farther apart. The few structures within them spread out even more. Over billions of years, this process makes the voids larger and emptier. Voids are not entirely uniform. They contain slight density variations, small galaxies, and minor flows of matter. But these small features do not change the overall nature of the void. Even the largest galaxies inside voids are isolated compared to galaxies in clusters. These isolated galaxies form in environments where interactions are rare. They evolve differently because they are not influenced by the gravitational forces created by nearby neighbours. Collisions, mergers, and tidal forces happen less frequently. These galaxies drift quietly, shaped mostly by internal processes rather than external interactions. When you look at the distribution of voids across the universe, they form a repeating pattern. Between every major filament or wall of galaxies, you find a void. These voids act as the open spaces in a vast network. They define the boundaries of the cosmic web. The filaments, clusters, and superclusters form the walls around them. The voids occupy the interior spaces. This arrangement gives the universe a foam-like structure when viewed on large scales, but unlike foam, the boundaries are not solid. They are composed of collections of galaxies connected by gravity. Some voids contain central regions that are even emptier than the outer parts. These central areas remain stable because matter has already moved outward. Gravity does not pull it back because the surrounding regions have stronger gravitational fields. Once matter flows toward the filaments, the void becomes permanently depleted. The expansion of space ensures the emptiness cannot be reversed. Even if a void galaxy were to move inward slightly, the expansion would push it outward over time. The largest voids maintain their emptiness because the expansion outpaces any minor gravitational effects within them. The shapes of voids reflect how they formed. They can appear elongated, flattened, or irregular. Some voids connect to others, forming continuous chains of low-density regions. Over time, smaller voids can merge into larger ones. This merging occurs naturally as galaxies migrate toward denser regions. The merging of voids does not create new structures. It simply expands the empty spaces. This process is part of how the universe becomes more spacious. The voids grow by absorbing neighbouring low-density areas, gradually becoming enormous cavities separated by long filaments of galaxies. Another interesting aspect of cosmic voids is how they influence the motion of galaxies in surrounding regions. Because voids contain less mass, they exert weaker gravitational pull. Galaxies near the edges of voids experience a net pull toward the denser regions around them. This effect pushes them outward from the void. As galaxies migrate toward filaments and clusters, the voids become even emptier. This outward drift is subtle but persistent. It continues as long as the nearby structures maintain higher density. Scientists study voids not just to understand emptiness, but to learn about the large-scale properties of the universe. The shapes, sizes, and distributions of voids provide clues about how matter evolved. They reveal information about the influence of dark matter and dark energy. They help show how the universe expanded at different times. Because voids amplify the effects of dark energy, studying them helps scientists measure how quickly the universe's expansion accelerates. The behaviour of galaxies in voids also reveals how gravity interacts with matter on the largest scales. Voids are surprisingly quiet in terms of interactions. Inside clusters, galaxies can collide or distort each other. Inside filaments, galaxies often influence each other's motion. Inside voids, these interactions are uncommon. The galaxies inside voids do not often form large groups. They rarely merge. Their paths are smoother. This lack of interaction shapes their evolution. Some void galaxies remain small for long periods because they do not encounter the conditions that trigger rapid growth. Others develop unique characteristics because they evolve in isolation. Their gas can remain undisturbed. Their star formation patterns can differ from those in denser environments. These differences help scientists understand how environment affects the development of galaxies. The temperature inside voids also tends to be lower, because they contain less matter to absorb and re-radiate energy. The few particles present are spread thinly. They do not heat easily. This low-density environment changes the behaviour of the cosmic microwave background as it passes through. The light shifts slightly due to the lower density. These shifts help scientists map the voids by analysing subtle changes in temperature across the sky. Another way voids influence the universe is through gravitational lensing. Even though voids lack mass, the absence of mass also affects how light bends. Light passing near a void travels along a different path than it would in a region of higher density. This slight difference creates distortions that can be measured. These distortions help identify the location and size of voids. They also help confirm the predictions of cosmological models. Because voids play such a significant role in defining the universe's structure, they also contribute to how galaxies flow across space. Galaxies at the edges of voids feel the pull of denser regions. They drift along paths defined by the surrounding mass. If you mapped the motion of these galaxies, you would see streams converging toward filaments and clusters. These streams outline the boundaries of voids. The structure is dynamic, even though it evolves slowly. The flows reveal how gravity continues to influence the universe on enormous scales. The existence of voids also helps explain why the universe appears as empty as it does when viewed from Earth. The night sky shows bright stars but hides the empty spaces between them. On larger scales, telescopes reveal that galaxies are widely spaced. On even larger scales, the structure of the cosmic web reveals long filaments and walls surrounding enormous voids. The voids dominate the map. The filaments form only a small fraction of the total volume. When you consider the distribution of everything in the universe, the matter that exists occupies only a small portion. The rest is empty space. The presence of voids also affects the future of the universe. As the expansion accelerates, the voids will widen. The filaments and clusters will remain intact because gravity holds them together. But the regions between them will stretch. The galaxies inside voids will drift farther from the filaments. Eventually, many galaxies in voids will become isolated from the cosmic web. They will remain alone, surrounded by expanding emptiness. The voids themselves will come to dominate even more of the universe's volume. Understanding cosmic voids brings you to a point where the structure of the universe becomes clearer. Matter gathers where gravity allows it. Darkness fills the surrounding space. The voids exist because matter moved elsewhere. They grow because there is not enough matter inside them to resist expansion. They define the background against which all structures exist. They help explain why the universe feels overwhelmingly empty, despite the presence of galaxies, stars, and planets. When you look at the structure of the universe as it exists today, with its clusters, filaments, and vast empty regions, it's natural to wonder how such a pattern began. The cosmic web seems almost too intricate to have appeared without a long history behind it. To understand why the universe contains so much emptiness, you have to go back to a time when emptiness didn't exist at all. The early stages of the universe looked nothing like the spacious environment you see now. Matter wasn't organised into stars or galaxies. Space wasn't spread across enormous distances. Instead, everything that would eventually make up the universe was compressed into conditions that are nearly impossible to imagine on human scales. In the very beginning, the universe didn't contain fire in the conventional sense. It contained temperatures so high that fire, as we understand it, would have been insignificant by comparison. In those earliest moments, the universe was a dense hot plasma, where particles couldn't form stable structures. Protons, neutrons, and electrons didn't exist as complete objects. Even the forces of nature weren't separate yet. They were unified under conditions so extreme that no familiar physical process could take place in the way it does now. As time progressed, the universe expanded rapidly. This expansion didn't occur into surrounding space. Instead, space itself grew. When space grows, the energy and matter inside it spread out. This spreading reduces the temperature and density. The early universe cooled in a way that eventually allowed particles to form, but this process took time. During the first fraction of a second, the universe experienced inflation, a dramatic period of accelerated expansion. Inflation smoothed out the early irregularities and created the first large-scale structure that would guide the universe's later evolution. These irregularities were incredibly small, but they were significant enough to determine how matter would gather billions of years later. After inflation ended, the universe continued expanding, but at a slower pace. As it cooled, particles like quarks and gluons began combining into protons and neutrons. These particles formed the first building blocks of atomic nuclei. The temperatures remained high enough to keep matter in a plasma state. Photons interacted constantly with charged particles, preventing light from travelling freely. The universe was opaque. The conditions resembled a uniform, dense fog where energy and matter remained tightly coupled. Over time, the universe cooled further. The density decreased as space expanded. This cooling allowed protons and neutrons to combine into the first light nuclei, primarily hydrogen and helium. A small amount of lithium formed as well. These early elements appeared within minutes after the beginning. But they didn't form atoms immediately. The universe stayed too hot for electrons to bind with the nuclei. It remained a bright plasma for hundreds of thousands of years. The early universe during this phase was filled with radiation. The photons travelled short distances before scattering off charged particles. This constant scattering kept the universe opaque. Nothing could pass through without being redirected. The matter remained evenly distributed because the temperature was too high for structures to form. But the small fluctuations from inflation still existed, waiting for the right conditions to grow. As the expansion continued, the temperature eventually dropped enough for electrons to combine with nuclei. This process is known as recombination. Once electrons were bound to atoms, the photons could travel freely. The universe became transparent. The light released during this transition remains detectable today as the cosmic microwave background. It provides a snapshot of the universe at a time when it was still mostly uniform, but contained the seeds that would eventually grow into galaxies, clusters, and voids. The transition from an opaque plasma to a transparent, cooling universe changed the dynamics of matter. Once atoms formed, gravity could begin influencing matter more effectively. The slight density variations left by inflation became the starting points for structure formation. Regions with slightly more matter started attracting additional matter. Regions with slightly less matter gradually emptied. This marked the beginning of the slow process that would eventually produce the large-scale structure of the universe. In the early universe, matter existed mostly as hydrogen and helium gas. This gas filled space uniformly, but wasn't stable. Gravity pulled the gas toward regions of higher density. Over millions of years, these regions grew denser. The gas cooled and collapsed into large clouds. Inside these clouds, small pockets of matter grew even denser, eventually forming the first stars. These early stars were massive compared to most stars today. Their enormous size caused them to burn quickly and emit intense energy. The formation of the first stars began transforming the universe from a uniform, gas-filled environment into a structured, evolving one. The stars ionized the surrounding gas, creating bubbles where radiation pushed matter outward. These bubbles expanded and merged, gradually breaking the uniformity of the early universe. The first stars also produced heavier elements in their cores. When they ended their lives in supernova explosions, they scattered these new elements into surrounding gas clouds. This enriched material became the seeds for later generations of stars and planets. The early stars also influenced how matter moved across space. Their radiation heated and ionized the gas around them, changing how easily the gas could collapse under gravity. Regions near the first stars experienced heating that prevented immediate collapse. Regions farther away could cool more easily. This contrast created variations that influenced the development of the cosmic web. The earliest galaxies formed when regions of matter became dense enough for gas to collapse into stable structures. These galaxies were small compared to the galaxies that exist today. They formed inside dark matter halos, which provided the gravitational well needed to hold them together. The halos guided the flow of matter and determined where galaxies could form. The structure created by dark matter during the early universe set the stage for the distribution of galaxies billions of years later. As galaxies formed and merged, they grew larger. Mergers were common in the early universe because the distances between galaxies were smaller. Collisions helped galaxies accumulate more stars and gas. But these mergers also influenced how matter distributed itself. When galaxies collided, their gas clouds could compress, triggering new waves of star formation. The stars themselves rarely collided because of the large distances between them. But the gas clouds acted as the raw material for growth. This early period of merging contributed to the diversity of galaxies that exist today. The early universe wasn't spacious in the sense that later structures became. Matter existed everywhere, and the distances between early galaxies were smaller. But even during this period, the seeds for emptiness were already present. The regions with less matter slowly expanded into voids as matter flowed toward the denser areas. These voids were not large at first. They grew as the universe expanded, gaining size as matter moved away from them. Over billions of years, the voids stretched into the vast empty regions we can see today. The cosmic web also began forming early. The filaments that now connect clusters of galaxies emerged gradually as matter followed the gravitational contours created by dark matter. These filaments formed the bridges that link galaxies. The spaces between them became the voids. This pattern, established early on, expanded with the universe. As the distances grew, the structure grew with them. The web remained intact because gravity continued guiding the motion of matter inside it. The early universe also experienced rionization, a process that took place after the first stars and galaxies formed. The intense radiation from these early sources rionized the hydrogen gas spread across space. This changed how visible the universe was to light. Regions filled with neutral hydrogen became transparent again as the gas rionized. This process marked a significant transition in the universe's evolution. It allowed light to travel farther and revealed the large-scale structures forming across space. The interplay between gravity, gas, and radiation shaped the early universe in ways that determine the modern structure. Gravity created the structures. Gas provided the material for stars. Radiation influenced how quickly the gas could collapse. These three components determined how quickly galaxies grew, how they interacted, and how the voids expanded. Even though the early universe started as a nearly uniform environment, these interactions built a complex framework that would persist through billions of years. As the universe continued to expand, the density of matter decreased. The expansion created new space. The distances grew, the early galaxies moved apart, the voids expanded, but the structure remained recognizable at larger scales. The cosmic web stretched, but it didn't dissolve. The pattern set by the early density fluctuations persisted. Ordinary matter followed this pattern. Dark matter deepened it. The expansion widened it. The result was a universe where emptiness became dominant not because matter disappeared, but because space grew faster than matter could fill it. Over time, galaxies evolved. The early population of massive stars gave way to more stable, longer-lived ones. The shapes of galaxies changed through mergers, interactions, and internal evolution. Spiral galaxies formed as gas settled into rotating disks. Elliptical galaxies formed as a result of mergers that randomized the motion of stars. Irregular galaxies remained where conditions were more chaotic. But regardless of type, all galaxies continued following the gravitational pathways created in the early universe. The early universe also provided the conditions that made life possible much later. The formation of heavier elements in early stars created the ingredients for planets. Without the early cycles of star formation and destruction, planets like Earth wouldn't exist. The hydrogen and helium created in the earliest minutes laid the foundation, but the heavier elements came from later events. The gradual build-up of these elements shaped the chemical environment of the universe. Even though the early universe was filled with matter, it didn't feel crowded in the way objects feel crowded in daily life. The plasma was dense by cosmic standards, but the distances between particles were still far smaller than the distances between stars today. As expansion continued, those distances grew. The universe transitioned from a dense, hot environment to a colder, more spacious one. This transition didn't happen suddenly. It unfolded over billions of years. As it unfolded, emptiness became more prominent. The story of the early universe is ultimately the story of how the modern universe's spaciousness began. The seeds for emptiness were planted early. Inflation created the initial distribution. Gravity deepened the contrast. Expansion widened the gaps. The combination of these processes shaped the environment in which galaxies formed and evolved. The same processes that created the structure also created the vast emptiness that dominates the universe today. When you follow the universe from its earlier stages into the vast structure that exists now, the emptiness on large scales becomes easy to visualize. You see the void stretching between filaments. You see clusters of galaxies surrounded by expanding space. You see how matter has gathered into narrow regions while the surrounding areas remain almost completely free of anything. But even after tracing this large-scale emptiness, there is another kind of emptiness that becomes important to understand. It exists not on the scale of galaxies or voids, but on the smallest scales the universe allows. When you look deeper than atoms, deeper than nuclei, and even deeper than the particles that form those nuclei, you find a kind of emptiness that behaves very differently from the empty space between galaxies. This emptiness is not silent in the way cosmic voids are. It behaves in a way that challenges the idea of nothingness entirely. The space inside an atom feels empty in a way that is easy to imagine. Atoms contain a tiny nucleus surrounded by a cloud where electrons are likely to be found. The distances between the nucleus and the surrounding electron cloud are enormous compared to the size of the particles themselves. If you scale an atom up to the size of a large stadium, the nucleus would be the size of a small grain in the centre, and the electrons would occupy the surrounding space without filling it. Most of the atom would contain nothing. This emptiness is not a flaw in the structure. It is a necessary part of how atoms exist. The forces and motions that create stability rely on this emptiness. Without it, atoms would collapse. But even the emptiness inside atoms isn't the end of the story. When you look at the smallest scales, the vacuum itself becomes more complicated than it first seems. You might assume that a vacuum contains nothing at all. No particles, no energy, no fields. But this assumption doesn't hold when you look closely. The vacuum isn't an empty container. It is a region where the fundamental fields of nature reach their lowest possible energy. These fields don't vanish in the vacuum. They continue to exist, and they continue to fluctuate. This means the vacuum is not truly empty. It contains activity even when it appears to contain nothing. Quantum physics describes the vacuum as a state that contains the lowest possible energy, allowed by the laws of nature. But this energy cannot be zero. The fields that fill space cannot be completely still. If they were, the uncertainty principles that define quantum behavior would be violated. The fields must fluctuate. They must change. These fluctuations create temporary particles that appear and disappear in extremely short periods of time. These particles don't behave like the particles you observe directly. They don't persist long enough to be detected in the usual way, but they influence measurable properties of matter. They shift energy levels in atoms. They affect the forces between particles. They even influence the expansion of the universe. This behavior shows that what appears empty is actually filled with activity. The empty space between particles, inside atoms, and throughout the universe contains fields that never turn off. Even when no particles are present, these fields remain. The fluctuations within them create brief disturbances that shape the behaviour of everything else. Nothingness, on the quantum level, becomes a background filled with constant motion. This might seem contradictory. You can look into space and see that large-scale regions contain almost no matter. But when you look at the vacuum on small scales, you find motion and energy that never stop. The emptiness between galaxies is silent because matter is absent. The emptiness inside atoms is active because the vacuum cannot be completely still. These two forms of emptiness coexist. They don't cancel each other out. They shape the universe in different ways. The large-scale emptiness determines how galaxies move. The small-scale emptiness determines how particles behave. One way to understand quantum nothingness is to look at the forces it produces. The Casimir effect is an example of how the vacuum influences physical behaviour. When two metal plates are placed extremely close together in a vacuum, they attract each other even without any charge or magnetism involved. This attraction occurs because the plates limit the wavelengths of vacuum fluctuations between them. More fluctuations exist outside the plates than between them. This difference in pressure pushes the plates together. The effect is small, but it is measurable. It shows that the vacuum contains energy and motion. These fluctuations exert real forces even without particles. Another example is the structure of atomic energy levels. The vacuum fluctuations shift the energy levels of electrons inside atoms. These shifts have been measured with high precision. They cannot be explained by classical physics. They occur because the electrons interact with the fluctuations in the vacuum. Even when the atom sits in empty space, the vacuum around it creates small adjustments that change its behaviour. This influence is subtle but constant. These fluctuations also help explain why particles have mass. In some theories, mass results from interactions with fields that exist throughout space. The fields don't disappear in empty regions. They fill all of space, even in the absence of matter. Particles interact with these fields, and this interaction influences how they move. The concept of mass becomes tied to the properties of the vacuum. Without the vacuum fields, the particles would behave differently. The empty space itself becomes a component of the physical properties of matter. The idea that the vacuum contains energy also connects to the expansion of the universe. Dark energy may be linked to the energy of the vacuum. If the vacuum energy remains constant, then as space expands, the total amount of vacuum energy increases. This increase could drive the accelerated expansion observed in the universe. Though this idea is still under investigation, it shows how the quantum nature of emptiness could influence the universe on the larger scales. The universe's accelerated expansion may be rooted in the smallest fluctuations of the vacuum. Quantum nothingness challenges the idea that emptiness is simple. Instead of being an absence, it becomes a foundation filled with constant activity. This activity isn't chaotic motion in the usual sense. It isn't something you could observe directly with the naked eye, but it has measurable effects. The vacuum becomes a medium where the laws of nature operate continuously. Particles emerge briefly and disappear. Forces arise from differences in the fluctuations. The properties of matter depend on how it interacts with the vacuum. When you move from the quantum scale back to the atomic scale, you can see how emptiness becomes even more essential. The stability of atoms depends on the structure of space. Electrons don't orbit nuclei the way planets orbit stars. Instead, they exist in regions where their probability of being found is described by wave functions. These wave functions extend through empty space. The empty regions inside atoms become part of the structure. They aren't areas where nothing exists. They are areas where the rules of quantum mechanics determine how matter behaves. These empty regions provide room for electrons to occupy stable states. Without the empty space, electrons would collapse into the nucleus. The structure of the atom requires emptiness. The vacuum's properties shape how the electrons move, how they absorb and emit energy, and how atoms bond to form molecules. This emptiness forms the basis of chemistry. It allows matter to combine, interact, and evolve. Even the structure of biological molecules depends on the emptiness inside atoms and between atoms. Without this emptiness, life could not exist. When you expand your perspective again to look at the empty space between molecules, you find even more room where matter doesn't exist. The distances between molecules are large compared to the sizes of the molecules themselves. This space allows matter to move, to vibrate, to conduct heat, and to change states. The empty space between molecules becomes essential for the behavior of gases, liquids, and solids. The emptiness allows motion. Without it, temperature, pressure, and sound wouldn't behave the way they do. When you continue moving outward to the empty space between stars, you find regions dominated by vacuum fluctuations and sparse particles. Even inside galaxies, most of the volume is empty space. The stars fill only a tiny fraction of the galaxy's volume. The rest is filled with low-density gas and the vacuum. The vacuum's quantum properties continue operating in those regions. Fluctuations occur everywhere. They don't disappear even when matter is absent. The emptiness between galaxies shows a different scale of nothingness. These regions contain even fewer particles, but the vacuum remains. The fields continue fluctuating. The vacuum energy remains constant. The expansion of the universe stretches these regions, increasing the amount of vacuum, but not changing its essential properties. The quantum fluctuations don't weaken as the universe expands. They remain present, influencing the behavior of matter and the shape of space. On the larger scales, the universe expands. On the smaller scales, the vacuum fluctuates. These two forms of motion coexist. They do not cancel each other. They shape different aspects of the universe's behavior. The large-scale emptiness depends on the movement of matter outward. The small-scale emptiness depends on the properties of the vacuum itself. The universe contains emptiness at every scale, but each scale has its own features and influences. When you consider these different scales together, the idea of emptiness becomes more complex. The emptiness inside atoms allows matter to exist. The emptiness between molecules allows chemistry and motion. The emptiness between stars allows galaxies to form. The emptiness between galaxies allows the universe to expand. And the emptiness of the vacuum influences all of these regions through fluctuations and fields. The vacuum becomes the foundation on which the universe builds everything else. Understanding quantum nothingness means seeing emptiness not as a lack of substance, but as a physical state with structure and behavior. The vacuum isn't empty. It contains the lowest energy configuration of fields. These fields remain active. They create motion. They influence matter. They affect forces. They shape the universe in ways that are not immediately visible, but they remain essential to understanding how the universe functions. When you spend time exploring the nature of emptiness in the physical universe, the next question that naturally appears has nothing to do with particles or galaxies, but instead with the way people react to the idea of emptiness itself. The concept of empty space, whether on the scale of atoms or on the scale of cosmic voids, has a psychological component that is difficult to ignore. Even if the science behind emptiness explains why matter is distributed the way it is, understanding how emptiness feels is a different subject entirely. Human beings evolved in environments filled with structure, surfaces, and boundaries. The empty regions of the universe do not resemble any situation that daily life prepares you for. This difference creates reactions that are often subtle, but consistent across people and cultures. The feeling associated with emptiness isn't just a matter of imagination. It connects to the way the brain processes space, distance, and the absence of familiar markers. When you look at a picture of a star field with only a few distant galaxies scattered across it, the scene can provoke a reaction that mixes curiosity and discomfort. That discomfort doesn't come from danger. It comes from the absence of context. The brain evolved to keep track of edges, sounds, motions, and potential threats in nearby surroundings. When confronted with an image or idea where there is almost nothing to track, the system that searches for patterns has little to work with. This mismatch creates a kind of quiet tension. The reaction to vastness is similar. Large spaces without boundaries challenge the parts of the brain responsible for orientation. When you walk through a forest, your senses register movement, shapes, textures, and sounds. Even when you stand in an open field, the ground beneath you and the sky above still provide reference points. But the void between galaxies contains no surfaces, no sounds, and no familiar cues. Thinking about such a space can evoke a response rooted in instinct rather than experience. The instinct expects orientation, and when orientation becomes impossible, the mind begins to search for stability. This search can produce unease because the usual methods for creating stability do not apply. This psychological response doesn't mean that emptiness is inherently frightening. It means that emptiness occupies a space outside the boundaries of human intuition. The same contrast exists on smaller scales. The fact that atoms contain so much empty space is not something you feel in daily life. But when you hear it described, it can produce a moment of surprise. The structure you interact with feels solid. It doesn't feel like a collection of particles separated by empty regions. When you learn that the solidity comes from forces rather than from filled volume, it can create a moment where your understanding of physical reality shifts. That shift can feel unsettling because it challenges assumptions developed through direct experience. The concept of nothingness itself is difficult for people to define. You can easily describe a room when it contains objects, but describing a room with nothing in it becomes more difficult. The walls and floor remain, but the content disappears. When the surroundings themselves are removed, leaving only open space, the idea becomes harder to grasp. The mind prefers defined shapes and boundaries. Emptiness lacks these features. This lack creates ambiguity. The brain evolved to reduce ambiguity by identifying patterns. When no pattern exists, the system continues searching. That ongoing search creates a feeling that something is missing. In the context of the universe, emptiness is not a deficiency. It is a natural result of how matter behaves. But the human mind doesn't interpret emptiness through the laws of physics. It interprets emptiness through the lenses of perception, memory, and evolution. People tend to associate empty spaces with isolation. When social contact decreases, the brain interprets the reduction as a potential threat. Early humans relied on group behavior for safety. Separation from others increased risk. This connection between emptiness and isolation lingers in psychological responses even in situations where the emptiness has nothing to do with social separation. This link becomes apparent when people look at images of deep space. The vast distances between stars represent a scale of isolation that cannot be experienced directly. The mind tries to relate this scale to familiar distances, but because the familiar distances are so much smaller, the attempt fails. The feeling of isolation arises from the failure to map the cosmic scale onto human-scale intuition. The brain responds to isolation whether it occurs physically or mentally. Thinking about enormous spaces can trigger the same systems that respond to being alone in an unfamiliar place. Another factor that shapes the reaction to emptiness is the difficulty of assigning meaning to it. Human cognition is built around identifying purpose, cause, and effect. Emptiness challenges these processes because it doesn't contain objects or actions that can be connected. When you look at a landscape on Earth, even an empty one, you can assign meaning. A desert contains sand dunes shaped by wind. A snowy field shows tracks from animals. The shapes and signs help the mind build a story. But the emptiness between galaxies lacks signs. It lacks evidence of processes that the senses evolve to interpret. Even though the scientific explanation exists, the immediate sensory interpretation does not. This gap shapes how people respond emotionally. In many cases, the reaction to emptiness becomes stronger when combined with scale. Small empty spaces like a clear room or a wide field rarely provoke deep discomfort. But when the scale increases beyond what the brain can easily imagine, the reaction changes. The emptiness begins to feel overwhelming because the mind cannot anchor itself. When scale becomes too large, the usual cognitive strategies lose effectiveness. The experience becomes unfamiliar, even if it is only imagined. The discomfort that follows isn't a sign of fear in the usual sense. It is a response to the absence of reference points. There is also an evolutionary reason for why people pay attention to empty spaces. Early humans needed to detect danger in their surroundings. An empty environment could hide threats. A quiet forest might signal the presence of predators. A silent plain might indicate that animals are avoiding the area for a reason. The brain develops systems that respond to silence and emptiness as potential sources of danger. These instincts persist even in modern life. When confronted with an unfamiliar emptiness, the brain's caution system activates. It doesn't know what to expect, so it increases alertness. This increased alertness explains why some people feel a quiet tension when thinking about the universe's vast emptiness. The response isn't tied to anything tangible. It isn't tied to risk. It is tied to the idea of an environment without familiar cues. The lack of cues activates the part of the brain that anticipates the unknown. Even if the unknown is not dangerous, the anticipation creates a sense of unease. This reaction is a byproduct of how the mind evolved, not a sign that the void itself contains anything harmful. Cultural influences also shape how people interpret emptiness. In some traditions, emptiness represents calm or openness. In others, it represents loss or absence. These interpretations influence how individuals respond emotionally when thinking about large empty spaces. A person who associates emptiness with peace might find the idea of cosmic void soothing. Another person who associates emptiness with lack might find them unsettling. These associations arise from experiences rather than from the physical properties of emptiness. Even in modern settings, emptiness shapes behaviours. People often avoid large empty public spaces because such spaces lack the social cues that help them interact comfortably. A crowded room offers opportunities for interaction. An empty room offers none. The mind interprets the difference quickly and adjusts behaviour accordingly. These reactions transfer easily to imagined empty environments, including those in space. When you consider why people fear heights, darkness, or deep water, the pattern becomes clearer. Each of these conditions removes familiar points of reference. The mind prefers stability and predictability. When surroundings don't provide those traits, internal systems that maintain a sense of security struggle to function normally. The emptiness of space behaves similarly. It represents a level of unfamiliarity that surpasses any direct experience the brain can rely on. The result is a reaction that blends curiosity with caution. Some people describe a sense of awe when thinking about the vastness of the universe. Awe is a complex reaction that combines surprise, scale, and the recognition of something beyond personal comprehension. This reaction is not entirely different from unease. Both reactions arise from the same absence of familiar boundaries. The difference lies in the interpretation. Awe sees the vastness as remarkable. Unease sees the vastness as difficult to process. The emptiness itself doesn't change. The reaction does. Another reason people fear emptiness is that emptiness challenges the sense of control. When you walk through a familiar environment, you can predict how things will behave. You know how far you can see. You know how sounds travel. You know how objects respond when moved. But the emptiness of cosmic space offers no such control. The scales involved are too large for the mind to manage. The distances make action impossible. Even imagining being inside such an environment exposes the limits of human capability. People tend to fear situations where control is lost or reduced. At the same time, emptiness can provoke feelings of insignificance. When confronted with something vast, the mind compares its own scale to the scale of the environment. In the context of the universe, the comparison is dramatic. The difference in scale creates a sense of being small. This feeling isn't harmful, but it can be uncomfortable. The mind prefers environments where it can find relevance. Cosmic emptiness provides none. That contrast can create an emotional response, but even though emptiness can evoke fear, it can also evoke calm. The absence of activity can feel peaceful in the right context. A quiet room can feel restful. An empty landscape can feel relaxing. Thinking about the void between galaxies doesn't necessarily produce fear. Some people view the emptiness as a natural part of the universe, no more threatening than the open sky. This variation in response suggests that the psychological effect of emptiness depends on individual interpretation, not on a universal instinct. When you understand the origin of these reactions, the unease becomes easier to interpret. The brain developed to handle environments filled with boundaries and sensory information. Emptiness removes these boundaries. It removes context. The mind responds by seeking patterns. When no patterns exist, the mind continues searching. This search creates tension. But once you recognize that the reaction is a byproduct of evolution rather than a reflection of danger, the emptiness can become easier to appreciate. Understanding the psychology behind emptiness helps explain why people react differently when thinking about the universe. Some feel overwhelmed. Some feel inspired. Some feel quietly reflective. These reactions show how the mind adapts to environments far outside the scale it evolved to handle. The void becomes a mirror for interpretation rather than a threat. The reactions come from within, not from the emptiness itself. When you spend time thinking about how people respond to emptiness, it becomes clear that the reactions are shaped by instinct, perception, and meaning. But once those reactions settle, another idea emerges that can feel almost counterintuitive. Even though emptiness can create discomfort or uncertainty, it also provides the conditions that make existence possible. Without emptiness, there would be no structure, no stars, no planets, no chemistry, and no life. The same emptiness that challenges intuition is the reason anything can form at all. The gaps between particles, atoms, stars, and galaxies are not failures in the universe's design. They are essential spaces that allow matter and energy to function in stable ways. To understand how emptiness enables existence, it helps to begin with the structure of matter on the smallest scales. The space inside atoms is enormous compared to the size of the particles themselves. This space isn't wasted. It allows electrons to occupy distinct energy levels without collapsing into the nucleus. If the electrons had no room to occupy, atoms would lose the structure needed to maintain their chemical properties. The empty space inside the atom provides the separation required for the forces that stabilize matter. Without that space, the universe would contain nothing resembling solids, liquids, or gases. Every object would collapse into a dense state where no complexity could form. This internal emptiness also allows atoms to bond with each other. Chemical bonds depend on the distribution of electrons in the space around atoms. Molecules form because electrons can occupy shared regions between atoms. The empty space allows the electrons to shift, interact, and settle into stable configurations. These interactions create the vast array of chemical structures needed for life. Proteins, DNA, and cellular structures all depend on these bonds. If atoms were tightly packed without empty space, these interactions would not be possible. Complex chemistry requires room for electrons to move and for atoms to form flexible arrangements. When you move from the scale of atoms to the scale of molecules, emptiness continues to play an essential role. Molecules interact through forces that depend on distance. Some forces attract, some repel. These forces require space to operate. The flexibility of molecules depends on the presence of space between their components. Biological molecules often have shapes that fold, twist, and change. These shapes function because of the empty regions around them. Without this room, the molecules would be rigid. Life depends on the movement and rearrangement of molecular structures. This movement depends on the presence of empty space. The internal structure of cells also relies on emptiness. A cell contains organelles, membranes, proteins, and countless molecules moving constantly. But most of the volume inside a cell is water and empty space where molecules drift. The cell structure depends on this space. Without it, essential processes like diffusion, energy transfer, and communication between molecules couldn't happen. Even the motion of molecules inside a cell depends on emptiness. If everything were packed tightly, the molecules wouldn't move freely enough to support life's functions. The space inside a cell may appear crowded, but it remains mostly empty, and that emptiness is vital. Emptiness also plays a role in the stability of larger structures. The space between atoms in a solid determines its rigidity. The space between molecules in a liquid determines its fluidity. The space between molecules in a gas determines how pressure and temperature behave. All the familiar states of matter are defined by the amount of emptiness inside them. Life depends on these states behaving predictably. Water flows because the molecules are not locked tightly together. Air compresses because the molecules have space to move. These behaviors depend on emptiness. When you leave the scale of molecules and cells and consider the environment needed for life, the importance of emptiness becomes even clearer. The space between stars provides the right conditions for planetary systems to form. If stars were too close to each other, their gravitational interactions would disrupt stable orbits. Planets would be pulled out of their paths or prevented from forming. The emptiness between stars provides enough separation for solar systems to develop in stable environments. This separation gives planets long periods of calm during which life can evolve. The emptiness inside galaxies plays a role too. Galaxies contain large numbers of stars, but the distances between them are enormous compared to their sizes. These distances are necessary to prevent frequent collisions. A galaxy filled densely with stars would be unstable. The gravitational interactions would create constant disruptions. The motion of stars would be chaotic. Planetary systems would rarely survive. The emptiness within galaxies provides the room needed for stars to move safely around their centres. This stability allows stars like the Sun to maintain conditions suitable for life over long periods. The space between galaxies offers another layer of protection. Galaxies move through the universe surrounded by wide regions of emptiness. If galaxies were closely packed, their interactions would disrupt their structures. Collisions between galaxies would be common. These events do happen, but the vast emptiness between galaxies limits how often they occur. The structure of the universe depends on this emptiness. It provides the room for galaxies to evolve separately without constant interference. When you consider how stars form, emptiness once again becomes essential. Stars form when clouds of gas collapse under gravity, but these clouds need space around them. If the universe were filled uniformly with dense matter, the collapse of gas clouds would not produce stable stars. The pressure from surrounding matter would disrupt the process. Instead, stars form in regions where gas has enough emptiness around it to collapse inward. The emptiness allows gravity to dominate in local areas, while the surrounding regions remain open. The life cycle of stars also requires emptiness. When stars release energy, their radiation spreads outward into space. This space must be empty enough for the energy to travel. If the universe were packed with matter, the energy would be absorbed quickly. The light from stars would not reach far. Life on planets depends on the steady flow of energy from their stars. Empty space allows that energy to travel without being blocked. The emptiness also allows heavy elements from supernova explosions to spread across the galaxy. These elements form new generations of stars and planets, including those capable of supporting life. Even the existence of planetary atmospheres depends on emptiness. An atmosphere forms when gravity holds gases around a planet. The gases occupy empty space above the planet's surface. This space allows weather patterns, temperature regulation, and the conditions necessary for life. Without emptiness, an atmosphere could not exist. There would be no room for the gases to move or form layers. The emptiness above a planet provides the environment for air, clouds, and climate. Life on Earth also depends on emptiness between Earth and the Sun. The distance creates the temperature range needed for liquid water. If the Earth were too close, the heat would boil away water. If it were too far, the water would freeze. The emptiness of space provides the room needed for planets to settle into stable orbits at the right distances. These orbits remain predictable, because the space around them is mostly empty. The stability of Earth's orbit, and the resulting stability of its climate, comes from this emptiness. The large-scale structure of the universe also creates environments where galaxies can form, stars can burn, and planets can support life. If the universe was smaller or packed with matter, the expansion would collapse quickly or never start. The emptiness allows expansion to continue. This expansion provides the necessary conditions for galaxies to spread out and evolve over billions of years. The expansion also prevents the continual collapse of matter into dense regions. Without the balance between gravity and emptiness, the universe would not have the diversity of structures needed for life. Another way emptiness supports existence is by preventing excessive interactions. If particles, atoms, or stars were too close together, interactions would become constant. High levels of interaction create instability. Life requires stable environments where changes happen gradually. Emptiness provides that stability. It prevents overcrowding and reduces conflict between forces. It allows matter to exist in arrangements that remain consistent over long periods. The concept of emptiness also supports time for evolution. Life takes immense periods to develop complexity. The universe must remain stable over those periods. The emptiness between stars and galaxies reduces the number of catastrophic events. It provides long stretches of calm. Even though stars evolve and galaxies change, the emptiness around them ensures these changes don't interfere constantly. This stability gives life the time it needs to develop, adapt, and diversify. The emptiness of the quantum vacuum also plays a role in existence. The fluctuations in the vacuum allow particles to maintain their properties. These properties influence how matter behaves. The vacuum structure supports the stability of atoms. It influences forces. It shapes the interactions that allow life to exist on every scale. Without the quantum properties of emptiness, particles would not behave in ways that support complex structures. The emptiness that exists inside living organisms also supports life. Cells rely on empty regions to transport molecules. They rely on empty spaces for chemical reactions to take place. They rely on water filling empty environments to help dissolve and distribute substances. The empty regions inside cells are not signs of inefficiency. They are the spaces where life functions. The machinery of life depends on separation, motion, and room to operate. Even the environment inside the human mind depends on a kind of conceptual emptiness. The ability to think, imagine, and reflect relies on mental space, where ideas can form without interference. The brain does not operate by filling every moment with signals. It operates by balancing activity with rest, noise with quiet, perception with reflection. Emptiness allows the mind to organize information and create meaning. When you put all of these examples together, the role of emptiness becomes clearer. Life exists not despite emptiness, but because of it. The gaps between particles allow atoms to exist. The gaps between atoms allow molecules to form. The gaps between molecules allow cells to function. The gaps between stars allow planets to orbit. The gaps between galaxies allow the universe to evolve. On every scale, emptiness supports structure, stability, and the conditions needed for life. This doesn't mean emptiness is a separate ingredient in the universe. It means emptiness is the environment in which everything takes shape. Matter relies on space. Motion relies on distance. Light relies on the absence of barriers. Life relies on the ability to grow, move, and adapt. These abilities depend on the presence of room. Emptiness is not the opposite of existence. It is a requirement for existence. When you understand how emptiness supports existence on every scale, the next step is to look forward and consider how the emptiness that surrounds everything will continue to grow. The structures that exist today are the result of billions of years of expansion. gravitational gathering, star formation, and gradual cooling. These processes have shaped the environment in which galaxies, stars, planets, and life exist. But the universe does not remain static. The emptiness increases with time, and this increase will continue far into the future. The spread of matter across widening distances will reshape what the universe looks like, how it behaves, and what remains visible. To understand the future of emptiness, you need to follow the effects of expansion, gravity, and time as they influence the universe on scales too large to experience directly. The expansion of space is one of the most important features driving the universe toward greater emptiness. This expansion is not caused by galaxies moving through space. It is the stretching of space itself. The stretching increases the distances between galaxies and clusters. When the universe was young, expansion happened more slowly because matter was dense enough for gravity to counteract it. But as matter spread out, the influence of gravity weakened. The density dropped. The expansion gained strength. Dark energy, the phenomenon responsible for the accelerated expansion, began to dominate the behavior of the universe. As dark energy's influence continues, the expansion of space increases the emptiness between structures more quickly. This means that the universe's future will involve increasing separation between galaxies and clusters. The galaxies inside each cluster will remain bound because gravity inside clusters is strong enough to resist expansion, but clusters will drift away from one another at an accelerating rate. Over billions of years, the distances between clusters will grow so large that the space between them will become almost entirely empty. From the perspective of an observer inside a cluster, the surrounding clusters will gradually fade as their light is stretched into longer wavelengths. Eventually, the light will stretch beyond detectability. The galaxies outside the observer's cluster will disappear from view, not because they vanish, but because the expansion pushes their light beyond the limits of observation. This process already affects the most distant galaxies visible today. Their light arrives stretched into the infrared. As the expansion continues, the stretching becomes more extreme. When you look into the deep sky, you're seeing galaxies as they were billions of years ago. You're also seeing the limit of what the expanding universe allows you to observe. In the far future, observers will see far fewer galaxies. The emptiness around them will appear even more complete than it does today. The night sky in those distant times will contain only the galaxies inside the local cluster, and eventually only the galaxies inside the remnant of the local group. The local group is the small collection of galaxies that includes the Milky Way, Andromeda, and several smaller galaxies. These galaxies are close enough to interact gravitationally. They are not governed by the expansion on these scales. Over billions of years, the Milky Way and Andromeda will move closer to each other and eventually merge into a single galaxy. The smaller galaxies in the group will also merge into this larger structure. After these mergers occur, the resulting galaxy will be surrounded by increasing emptiness as the expansion carries all other galaxies farther away. The local group will become an isolated island of matter in a universe that continues to grow. Inside this isolated island, life could continue for a long time. Stars will continue burning. New stars will form from the remaining gas. The merged galaxy will settle into a stable structure. But outside this merged structure, the emptiness will deepen. The distances will grow so large that the surrounding universe will become invisible. Future astronomers living inside this isolated system might not be able to detect evidence of cosmic expansion. The clues that scientists use today to understand the universe's history would no longer be present. The cosmic microwave background would be stretched into wavelengths too large to detect. The distant galaxies would be gone from sight. Without these clues, the understanding of the universe's origins would become more difficult. As the expansion continues over tens of billions of years, new stars will continue forming, but the supply of gas will decrease with time. Each generation of stars uses some of the gas and transforms it into heavier elements. The remaining gas becomes more limited. Star formation slows. the overall brightness of galaxies decreases. The emptiness inside the galaxy increases because the regions where gas once moved freely become quieter. Star formation shifts to smaller pockets. Over hundreds of billions of years, star formation will decline significantly. The remaining stars will be long-lived, dim stars that burn slowly. These stars will last for trillions of years, but the overall brightness of the galaxy will diminish. The emptiness between the stars will remain vast. Future observers living in such an environment would see a galaxy that glows faintly in a universe that contains almost nothing beyond it. As time progresses even further, the stars inside galaxies will begin to fade. The longest-lived stars will eventually exhaust their fuel. White dwarfs will cool. Neutron stars will remain, but they will emit little energy. Black holes will continue to exist, but they will not provide light. The galaxy will become darker. The emptiness between the dark objects will increase in significance. The universe will enter an era where very little light remains. The structures that defined the earlier periods will fade into near invisibility. The expansion will continue during all of these stages. The distances between the isolated galaxies will increase so much that even if a signal could be sent, it would never reach another galaxy. The emptiness will dominate not only the physical structure, but the possibility of communication or interaction. Each galaxy or merged cluster will remain alone. The future universe will be made up of isolated islands surrounded by a vast sea of emptiness. Over even longer timescales, the galaxies themselves will change further. The orbits of stars inside galaxies could eventually shift due to interactions with dark matter and gravitational fluctuations. Some stars may be ejected into the outer regions of their galaxies. The emptiness inside the galaxy will grow. Some of the stars pushed outward may drift beyond the gravitational influence of the galaxy entirely, entering the expanding universe. These stars will fade into the darkness, leaving the galaxy with fewer components. Eventually, the matter inside galaxies may settle into long-term configurations where little activity remains. The universe will become quiet. The emptiness will become complete enough that the remaining objects will exist in isolation. Even the black holes inside galaxies will eventually lose energy. Over extremely long periods, they will release energy through processes predicted by quantum physics. These processes are slow, but over vast timescales, they lead to the gradual disappearance of black holes. As this happens, the mass within galaxies decreases further. The emptiness becomes even more dominant. Throughout these transformations, the expansion of the universe continues shaping the overall picture. The empty regions become larger. The structures become smaller and more isolated. Time stretches these processes across unimaginable durations, but the direction remains consistent. The emptiness grows. The matter becomes increasingly sparse. The forces shaping the universe continue working, but the structure becomes more diffuse. Even though the universe will become lonelier, it does not become completely inactive. Particles continue moving. Space continues expanding. Quantum fluctuations continue. But the large-scale structures become quiet. The dramatic events that shape the early universe become rare. The emptiness becomes the most significant feature of the cosmic environment. The universe that once contained bright galaxies, active star formation, and dense clusters becomes a universe filled with long stretches of quiet space. This long-term future is shaped by the same processes that created the structure of the universe in the first place. Expansion created the initial separation. Gravity shaped matter into stars and galaxies. Dark energy accelerated the expansion. Time extended the changes. The same elements that created the universe's early structure continue defining its distant future. The emptiness that grows in the future becomes a natural extension of what began long ago. Even though the future of the universe involves increasing emptiness, this doesn't change the significance of the structures that exist now. The stars that formed, the galaxies that evolved, and the planets that developed life all emerged during a period when the universe had the right conditions. Those conditions included enough empty space to allow matter to gather, but not enough to prevent interactions. The era that supports life is a narrow period in the history of the universe. It exists between the dense early stages and the sparse future stages. The emptiness that grows later doesn't diminish the value of the time when the universe was filled with structure. When you think about the future of emptiness, it reflects the direction of the universe, but not the meaning of the structures that have existed. The growth of emptiness is part of the universe's natural evolution. It is not a decline. It is an expansion of the environment that has always been present. The emptiness of the future continues the trend that has existed since the beginning. When you follow the story of emptiness from the smallest scales to the farthest reaches of the universe, the final piece to explore is how that emptiness fits into a broader sense of understanding. All throughout this journey, emptiness has appeared as something that supports structure, offers room for formation, and shapes the environment from the earliest stages of the universe to the distant future. It has never been a flaw or a mistake. It has been an essential feature that allows everything to exist. But beyond the physical details, there is a quieter question beneath all of this. It concerns how to relate to the idea of emptiness, not only as a scientific concept, but as something that can feel unsettling or unfamiliar. The story of emptiness becomes easier to accept when it's understood as a natural part of the universe's behaviour. This understanding can gradually shift from curiosity to comfort. When people first encounter the idea that the universe is mostly empty, the reaction can feel sharp or disorienting. It might seem strange that nearly all matter is separated by enormous distances, and that even the matter itself contains empty regions inside it. These ideas challenge day-to-day experience where everything feels solid, connected, and filled. But once the initial reaction settles, the idea of emptiness can be approached with a different kind of clarity. You start to see that emptiness is not an absence of meaning. It is part of the framework that makes everything else possible. Without emptiness, there would be no space for anything to move, function, or evolve. The universe would not support the variety of structures that give it depth and complexity. Getting used to this idea takes time. You might begin by looking at the night sky and noticing how the brightest points appear, separated by large areas of darkness. These dark areas are not barriers. They are windows into the wider universe. They show the scale of the environment in which galaxies exist. Even though the distances can feel overwhelming, they indicate how the universe functions on large scales. The darkness between stars is the space that allows stars to orbit without disruption. The quiet between galaxies gives galaxies room to form and evolve. Seeing emptiness as part of a functioning system helps soften the reaction to its scale. The same shift can happen when thinking about the emptiness inside matter. The idea that atoms are mostly empty space can feel unusual at first, but once you understand that this emptiness is required for atoms to hold their form, bond with each other, and create stable structures, the strangeness begins to fade. The emptiness becomes a structural necessity rather than an unexpected absence. You begin to see that emptiness is not a lack of content, but the environment in which content becomes stable. The electrons, protons, and neutrons behave in a way that relies on available space. Their movement, their interactions, and the forces binding them all depend on emptiness. This perspective can extend to the space inside cells, inside organs, and inside living bodies. Life itself doesn't form by packing everything tightly. Life forms by creating room for chemical reactions and biological processes to function. Motion, metabolism, and communication between molecules depend on space. The emptiness inside cells is not a flaw in their design. It is part of what allows them to remain dynamic. Without that space, life would not adapt or respond. It would collapse into immobility. Recognizing this shifts emptiness from something uncertain to something essential. The emptiness surrounding planets also supports stability. The Earth orbits the Sun because the surrounding space gives it room to follow its path. The emptiness protects the atmosphere from constant disruptions. The sunlight that reaches Earth travels through empty space. The gentleness of morning light, the gradual shift of seasons, and the steady rotation of the planet all rely on the emptiness around it. This awareness can create a sense of connection instead of distance. The emptiness becomes part of the environment that supports daily life, not something separate from it. When you look at the universe as a whole, emptiness appears in every layer. It acts as a quiet foundation that never draws much attention but always plays a role in shaping what exists. Once this becomes clear, the sense of unease begins to soften. You start seeing emptiness as part of the balance that allows matter to gather, stars to burn, and planets to form. The fear connected to emptiness often comes from unfamiliarity. As the unfamiliar becomes more understandable, the emotional response shifts. The mind can settle into a calmer view of the large spaces that hold galaxies and the small spaces that hold atoms. The future of the universe, filled with increasing emptiness, might seem like a story heading toward isolation. But even that perspective changes with a broader understanding. The expansion of the universe does create greater distances. It causes galaxies to drift apart and eventually fade from each other's view. But this doesn't erase the significance of what exists now. The structures that formed, the stars that burned, and the planets that developed life emerged during a period when the universe contained the right balance between matter and emptiness. This balance produced environments stable enough for life to grow. The increasing emptiness of the future does not diminish the era in which life exists. It simply shows the larger pattern of how the universe evolves. Finding comfort in the idea of cosmic emptiness doesn't require ignoring its scale. It involves recognizing how it fits into the broader story. The universe has always transitioned through different stages. It began densely packed. It expanded into a form where matter could gather and create structure. It continues expanding into a future dominated by quiet distances. Each stage has its own character. The emptiness that appears in the distant future reflects the long-term behavior of space, matter, and energy. These processes are not abrupt or disruptive. They unfold slowly, over times far longer than any human scale. Understanding this gradual movement helps the idea feel less overwhelming. Another step toward finding comfort in emptiness involves recognizing that emptiness does not erase connection. Even though distance increases, the connections created through shared origins remain. Every atom in every person formed in stars, and those stars formed from the earliest elements in the universe. The emptiness between stars and galaxies does not break that connection. It shows how widely matter has spread. Emptiness becomes part of the story of how matter has travelled, gathered, and changed. The distances do not separate this history, they reveal it. In everyday life, emptiness also provides balance. Moments of quiet allow the mind to settle. Spaces between thoughts create clarity. The time between experiences allows reflection. Just as the universe uses emptiness to maintain stability, people use emptiness in their own internal rhythms. These moments of space support focus and understanding. Recognizing this parallel between the personal and the cosmic can bring the idea of emptiness closer to something familiar. It becomes less like a distant concept and more like a natural part of how things function. The ability to find comfort in emptiness grows as the idea becomes more integrated. Instead of seeing emptiness as a symbol of absence, you start seeing it as the framework supporting everything else. Without empty space, matter would have no room to move or change. Without empty space, the universe would remain static. Without empty space, life wouldn't have the stability it needs to evolve. The emptiness that surrounds everything provides the room for existence to unfold in all its forms. This realization doesn't remove the scale of emptiness. The distances between galaxies remain vast. The empty regions inside atoms remain extreme when compared to the size of the particles. But the meaning attached to that emptiness changes. Understanding replaces uncertainty. Knowledge replaces unfamiliarity. The spaces that once appeared unsettling begin to feel natural. They become part of a functioning universe, rather than something separate from it. As the universe continues its expansion, emptiness will grow, galaxies will drift farther apart, stars will burn through their fuel, the night sky will become quieter. But these changes will happen slowly, over times far longer than the era in which life emerges. The universe will continue its gradual movement toward greater distances. This future does not diminish the present. It highlights the brief period in which the universe supports complex structures. It shows that the universe has many phases, each with its own characteristics. When seen through this broader lens, the emptiness that exists now takes on a different quality. It becomes part of a long story rather than a frightening void. It shows how the universe accommodates motion, change, and structure. It provides the environment where stars can shine and where planets can develop life. This perspective can bring a sense of calm. The emptiness isn't something to escape, it's something to understand. With this understanding, the idea of emptiness becomes something that can be approached with steadiness rather than hesitation. The emptiness between galaxies, stars, atoms, and particles is not a barrier. It is a condition that allows the universe to function. It supports the movement of light, the formation of matter, and the stability of structures. It is part of everything. Recognizing this helps bring the idea into a more familiar place within the mind. As the exploration of emptiness reaches its quiet conclusion, the thought that remains is that emptiness has always been present, shaping the universe from its earliest moments. It continues to influence everything that exists now. It will remain part of the universe far into the future. Emptiness is not separate from existence. It is one of the conditions that makes existence possible. Understanding this brings a sense of clarity that replaces the initial unease. It offers a way to see the universe as a balanced system where emptiness and matter work together. The emptiness that once felt distant becomes something that can be viewed with calm. The idea settles into place. The universe is filled with wide spaces, quiet regions, and long distances. But within those spaces, matter forms, stars burn, planets orbit, and life develops. Emptiness allows all of it to happen. And when viewed through that understanding, the emptiness that surrounds everything begins to feel less like nothing, and more like the quiet structure that holds the universe open for everything it contains.